Hello and welcome to Sleepy Science. What if reality does not break in fantasy, but in experiments so real, so precise, and so repeatable that they make the world itself feel impossible? What if a quantum object can reveal a bomb without setting it off? A detector can destroy a pattern without touching the screen. Silence can become information, and a single particle of light can slowly build a wave-like image all by itself. In this 4-hour journey through quantum experiments that make reality feel impossible, we'll move gently through 30 real discoveries that challenge the most ordinary ideas of seeing, measuring, touching, and knowing, not as myth, not as speculation, but as carefully tested science from the strange edge of modern physics. We'll explore light that splits, reunites, and vanishes, photons that behave as if they know too much, atoms that reveal hidden states through silence, and machines so sensitive they turn quantum weirdness into something scientists can actually control. And as you settle into this journey, tell me in the comments, where are you watching from and what's the local time there? If this quiet exploration helps you think a little deeper, don't forget to like the video and subscribe so you can return for more calm journeys into science, reality, and the strange questions hiding beneath ordinary life. So take a slow breath, let the noise of the day soften, and step into the experimental world of quantum physics, where absence can answer, measurement can reshape possibility, matter can behave like a wave, and the universe reveals that what we call real may depend on questions far more delicate than we ever imagined. A quantum object can reveal a bomb without exploding it. Some discoveries do not begin with a flash, a crash, or a dramatic signal. Some discoveries begin with something stranger, an event that should have happened but didn't. Imagine a sealed box sitting quietly on a table. Inside it, there may be a bomb so sensitive that even a single particle of light touching its trigger would make it explode. You cannot open the box. You cannot shake it. You cannot shine ordinary light inside. You cannot test it directly because the very act of testing could destroy the thing you are trying to understand. In the everyday world, this sounds like a dead end. To know whether something is there, you have to touch it. To know whether a bomb works, you have to risk setting it off. Knowledge seems to demand contact. Evidence seems to require collision. But quantum physics opens a door that feels almost impossible at first. Under the right conditions, you can sometimes discover that something is present because of what did not happen. You can learn from the path a particle never took. You can gain information from the explosion that never came. You can hear reality answer through absence. This is the strange idea behind the Elitzer-Vaidman bomb tester, proposed in 1993 as a thought experiment in what physicists call interaction-free measurement. The word bomb makes it sound dangerous and theatrical. But the real point is not about weapons. The bomb is a symbol for any fragile object that would be destroyed if a particle actually touched it. The deeper question is this: can the quantum world reveal the presence of something without the usual direct impact? And the answer, in certain carefully prepared situations, is yes. To understand how, picture a single photon, a tiny packet of light, entering a device called an interferometer. This device can split the photon's possible route into two paths. If you imagine the photon like a tiny marble, you might think it simply chooses left or right. But a photon is not a marble. When no one checks which path it takes, quantum physics allows its possibilities to behave more like overlapping waves. The two possible paths can later meet again, and when they meet, they can interfere with each other. This interference is not just a metaphor. It decides where the photon can be detected. In a perfectly arranged setup, when both paths are open and undisturbed, the photon always reaches one detector and never reaches another. That second detector is called the dark detector because, under normal conditions, it should remain silent. No click, no signal, nothing. Its silence is part of the design. Now the strange part begins. Place the sensitive bomb in one of the two paths. If the bomb is real and working, then one possible route has become dangerous. If the photon takes that route, the bomb absorbs it and explodes. But if the photon does not take that route, something just as important changes. The mere fact that one possible path was blocked destroys the perfect interference between the two paths. The photon's possibilities can no longer recombine in the same clean way. And because that perfect pattern has been disturbed, the detector that was supposed to stay dark can suddenly click. That click is the clue. It tells you that the working bomb was present in the other path, but the photon was not absorbed by it. The bomb did not explode. The trigger was never touched, and still, information was gained. Nothing hit the bomb, yet the experiment learned that the bomb was there. This is what makes the idea so haunting. The photon does not magically know the bomb exists. It is not mind-reading, and it is not a trick for seeing through walls. It is a real consequence of quantum interference. The photon's final behavior depends on the full arrangement of possibilities available to it. When one possibility is removed, the whole pattern changes, even if the photon is never actually found on the blocked path. In ordinary life, that feels backwards. We are used to evidence coming from contact. A fingerprint on glass, a sound behind a wall, a footprint in wet ground. But here, evidence comes from a missing path. It is as if reality says, something was there. Not because it was touched, but because it changed what could have happened. In the simplest ideal version, this method does not succeed every time. Sometimes the bomb explodes. Sometimes the result tells you nothing useful. But sometimes the dark detector clicks, and in that successful case, you identify a working bomb without detonating it. Later work, including experiments and improvements by Kwiat and colleagues in 1995, showed that the efficiency of this kind of measurement could be increased using repeated, gentle tests. So the idea is not just a beautiful puzzle. It became part of real experimental quantum physics. But it is also important to stay honest about what the phrase interaction-free really means. It does not mean information comes from nowhere. It does not mean the object has no role in the experiment. The bomb changes the conditions because it is available as a possible absorber. In the successful case, the surviving photon does not strike the bomb, but the bomb's presence still reshapes the quantum possibilities. That is the subtle beauty of the experiment. It does not say, you can know everything without consequence. It says something much more precise and much more interesting. Under the right conditions, what might have happened can leave a trace on what actually happens. And that is why this experiment feels so different from ordinary measurement. Usually, we think of measurement as an act of force. We shine light, we touch, we cut, we open, we disturb. But here, reality is questioned more gently. The experiment is arranged like a careful trap for possibility itself. If the dark detector remains silent, you may learn nothing. If the bomb explodes, you learn the hard way. But if that impossible little click appears in the detector that should have stayed quiet, then silence has spoken. A danger was present, a path was blocked, a possibility was removed, and the universe left a signal in the shape of that absence. This is where the science becomes more than a clever mechanism. It changes the way you think about knowing. A thing does not always have to shout to be real. Sometimes it changes the pattern around it. Sometimes it announces itself by preventing something else from happening. Sometimes the most important evidence is not the collision, but the missing collision. Of course, human life is not a quantum interferometer, and emotions do not obey the same rules as photons. But the experiment gives us a quiet metaphor that still feels deeply human. Absence is not always empty. A closed door can change the hallway. A silence can change the meaning of a question. A path not taken can still shape the place where you arrive. And in the quantum world, this is not only poetry, it is physics. A photon enters the device. A bomb waits in one possible path. No explosion comes. A detector clicks where no click should be. And from that single click, you learn that something unseen was there. Not because it was touched, not because it was destroyed, but because its possibility changed the pattern of reality. At the end of this strange doorway into quantum measurement, the bomb remains unexploded. The photon survives, and your old idea of evidence feels a little less solid than before. Because quantum physics has shown you something gently unsettling. Sometimes reality reveals itself not through impact, not through force, not through direct contact, but through the shadow an unseen thing casts across possibility. You can measure something by not seeing it. What if a detector could measure something not by flashing, but by refusing to flash? Imagine you are standing in a quiet laboratory late at night, watching a screen that is supposed to light up if a tiny quantum object passes through a certain region. The room is still, no sound, no spark, no signal. In everyday life, that would usually mean nothing happened. You waited and the machine stayed quiet. But in quantum physics, that silence can become part of the measurement, not a mistake, not missing data, a real result. The detector's failure to click can tell you something about the object, and in some cases, it can even help change the object's quantum state. This idea is called a negative result measurement, and it carries one of the strangest lessons in quantum theory. Information does not always arrive as a visible mark on a screen. Sometimes it arrives as the mark that never appears. To understand this gently, imagine a single particle that could be in one of two places, almost like a whisper spread between two rooms. You place a detector in only one room. If the detector clicks, you know the particle was there. That part feels normal. But if the detector does not click, you still learn something. The particle was not found in the watched room, so the other possibility becomes more important. In ordinary thinking, this sounds simple. Maybe the particle was just hiding somewhere else all along. But quantum physics is stranger than that. Before the measurement, the particle may not have been simply here or there in the usual sense. Its state could involve both possibilities at once. When the detector has the chance to respond and remain silent, those possibilities are narrowed. The object's description changes because of what did not happen. That is the unsettling part. The quiet detector is not just sitting outside the story. It becomes part of the physical situation. It was active. It was ready. It was placed where a signal would have appeared under one condition. And because no signal appeared, that condition can be ruled out. This is very different from ignorance. If you close your eyes and fail to see a bird fly past, you have not measured anything. But if you set up a sensitive camera aimed at the only window the bird could pass through, and the camera records nothing, that absence means something. The experiment was prepared to answer a specific question. When the answer does not arrive in the expected way, the silence itself becomes useful. In quantum mechanics, this idea reaches deeper than ordinary detective work. A no-click result can do more than update your knowledge. It can help define which quantum possibility remains. The detector does not need to catch the particle directly in order to affect the story. It only needs to create a situation where one possible outcome would have produced a signal. When that signal fails to appear, the remaining state becomes sharper. It is as if the world has quietly said, "Not there," and by removing that option, it changes what can still be true. Physicists have thought about this for a long time. Moritz Renninger explored early versions of this idea, asking how a particle's state could be affected even when it was not directly detected. Later, similar principles appeared across many quantum experiments. The core idea is simple but powerful. If a system is arranged so that a detector would have reacted under one condition, then no reaction can rule that condition out. The absence is meaningful because the experiment gave nature a clear chance to leave a trace. This does not mean every silence matters. Most silences are just silences. A detector that is turned off tells you nothing. A detector in the wrong place tells you very little. A blank screen is not automatically profound. The meaning comes from the setup. The detector must be active, sensitive, and positioned so that a specific event would produce a clear result. Only then can its silence become an answer. Science is careful here. It does not say absence is always evidence. It says absence can become evidence when the conditions are designed correctly. And that distinction is what makes the idea so beautiful. Quantum measurement is not simply about a human eye looking at the world. It is not about consciousness magically creating reality. It is about physical systems becoming connected to possible outcomes. If the detector could have become correlated with the particle being in one place, but does not, then the remaining quantum description changes. Not because your mind invented the result, but because the experimental world filtered the possibilities. This is why negative result measurement feels so different from everyday observation. We usually imagine measurement as contact. We shine light, we touch, we open, we listen, we wait for impact. But quantum physics teaches a quieter grammar. Measurement can also be the careful elimination of alternatives. A missing signal in the right context can be just as meaningful as a signal that appears. The detector does not shout. It simply remains silent in a situation where silence should not be ignored. There is a simple way to feel the strangeness of it. Picture walking along a snowy path at dawn. You look near one gate and find no footprints. In ordinary life, that tells you someone probably did not walk through that gate. But in the quantum world, the missing footprint can do more than inform you after the fact. It can help decide which version of the story remains available. The absence is not passive. It participates. This idea also touches the quantum Zeno effect, another strange phenomenon, where repeatedly checking whether a quantum system has changed can slow down or even prevent that change. The surprising part is that the repeated checks do not always need to find a dramatic event. The continued confirmation that something has not happened can still influence how the system evolves. Again, reality is shaped not only by what appears, but by what is ruled out. There is something almost meditative in this, even though the science is precise. The quantum world does not always announce itself with collisions, flashes, or explosions. Sometimes it works through constraints, through excluded paths, through possibilities trimmed away until one remains. And once you understand that, the word nothing begins to feel less empty. Nothing happened at the detector, yes, but that nothing had structure. It had a question built into it. It was not blank. It was an answer shaped like silence. This is why the idea stays with you. It changes the way you think about knowing. Is knowledge always something that appears in front of you? Or can it also come from the disciplined recognition that one possible result failed to occur? Is reality made only from events, or also from the non-events that shape them? In human life, we often overlook absence because it feels less dramatic than presence. We notice the words spoken more than the words withheld. We notice the door that opens more than the one that never does. We notice the alarm that rings, not the danger that quietly fails to arrive. Of course, human life is not a quantum experiment, and emotions do not obey the rules of particles. But the metaphor is still powerful because it is grounded in real physics. Absence is not always empty. Sometimes it has a shape. Sometimes it carries information. Sometimes what does not happen changes everything that can happen next. So when you hear that quantum physics can measure something by not seeing it, do not imagine magic. Do not imagine a shortcut around evidence. Imagine something stranger and more careful. A world where possibility itself is part of the machinery, where an active detector can learn from a missing signal, and where a blank screen, watched under the right conditions, can become one of the most delicate instruments science has ever used. Light can be split, rejoined, and made to vanish. A beam of light can be made to vanish, not because something blocks it, not because it is swallowed, and not because its energy disappears, but because it meets another version of itself at exactly the wrong moment. At first, that sounds almost impossible. Light feels like the most honest thing in nature. A lamp turns on, and the room brightens. A laser touches a wall, and a red dot appears. Sunlight slips through a curtain, and dust begins to glow in the air. Light seems direct, simple, dependable. It arrives, and the world becomes visible. But in a carefully arranged experiment, that familiar simplicity begins to break open. You can take a beam of light, send it toward a special mirror called a beam splitter, divide its journey into two separate paths, guide those paths around different arms, and then bring them back together again. And when the reunion is arranged with extreme precision, something strange happens. One exit can become bright, while the other becomes dark. The light has not been destroyed. Nothing has gone missing. The universe has not lost track of its energy. Instead, the returning waves have cancelled each other in one direction, like two ocean ripples meeting crest to trough and flattening the water between them. This is called destructive interference, and it reveals one of the quietest mysteries of light. Sometimes brightness can be shaped by cancellation. To feel the idea gently, imagine two singers holding the same note. If their voices rise and fall together, the sound grows stronger. But if one voice pushes the air forward at the exact moment the other pulls it back, the sound can weaken, almost as if one voice has erased the other. Light can behave in a similar way, though it is not made of vibrating air. It is an electromagnetic wave, carrying rhythm, timing, and phase. When two parts of the same light wave meet again, their peaks and dips can either reinforce each other or cancel each other, depending on how perfectly they line up. In a device like the Mach Zehnder interferometer, this is not random. The mirrors and beam splitters are arranged so carefully that the returning light follows a predictable pattern. One output becomes bright because the waves add together there. The other output becomes dark because the waves subtract from each other there. And that darkness is not failure. It is not emptiness. It is a pattern made visible by the absence of light. This is the important point. The light does not vanish everywhere. It only vanishes from one particular direction. Energy is conserved. What disappears from the dark exit is redirected into the bright one. The mystery is not that light is destroyed, but that light can be guided by a relationship. The result depends not only on where the beam travels, but on how its divided parts return to each other. Move a mirror by a tiny amount, place a transparent material in one path, or slightly change the distance one part of the light must travel, and the entire outcome can shift. The dark exit may brighten, the bright exit may dim. A change too small for your eye to notice can reshape the final pattern, because light remembers timing with extraordinary sensitivity. The beam splitter is the doorway into this strangeness. With an ordinary bright beam, it is easy to imagine some of the light going one way and some of it going another. That picture is useful enough when many photons are involved. But when the experiment is dimmed until only one photon enters at a time, the story becomes far more delicate. You never detect half a photon at one detector and half at the other. A photon arrives as one whole event, one click, one place, one result, and yet the probabilities of where that photon appears are shaped as though its wave-like description has traveled through both arms of the interferometer. That is what makes the experiment feel so unsettling. Light is detected like a particle, but it moves through the experiment according to rules that allow interference. It is not simply a tiny glowing pellet choosing a road. It is not simply a wave smeared everywhere in the ordinary sense. It is something stranger, a quantum object whose possible histories can be split, guided, recombined, and made to decide where it can appear. This is why the dark exit matters so much. If light were only a stream of tiny bullets, splitting the path and bringing it back together would not create this precise vanishing act. But because light has phase, because its wave-like possibilities can meet in step or out of step, the final result depends on the arrangement. The same photon that could have appeared in one detector is steered away from it by interference, not by a wall, not by a hand, not by a hidden force pushing it aside, by the structure of possibility itself. The experiment does not merely ask, which path did the light take? It asks something deeper. How do the possible paths relate when they meet again? That question is not only philosophical. Interference is one of the most powerful tools in modern science. Interferometers can measure incredibly tiny changes in distance, vibration, thickness, and phase. They appear in optical technology, quantum experiments, precision sensors, and even in the enormous instruments used to detect gravitational waves. Anti-reflective coatings on lenses also use interference. Reflected waves can be arranged to cancel, reducing glare and allowing more light to pass through. So this strange ability of light to disappear from one direction is not just a laboratory curiosity, it is a practical language. It lets scientists turn almost invisible changes into measurable signals. The darkness is not useless, it is information, and still, beneath the practical power, there is a deeper wonder. What does it mean for something real to cancel itself? You are used to thinking that adding more should produce more. More light should mean more brightness. More evidence should mean more certainty. More presence should mean less absence. But waves teach a different rule. Sometimes adding can subtract. Sometimes two presences can meet in such perfect opposition that they create darkness. The result does not depend only on how much exists, but on how things are aligned. Phase matters. Timing matters. Relationship matters. Two beams made from the same source can travel different routes, return together, and disagree so precisely that one direction goes dark. That darkness is not empty. It carries the hidden memory of both paths. It contains the precision of their meeting. It is shaped by the distances traveled, the mirrors adjusted, the phases compared. It is not the darkness of nothing being there. It is the darkness of something being arranged so perfectly that it cancels itself from view. And this is where the experiment begins to change the way you think about reality. The world is not only made of isolated things moving alone through space. It is also made of relationships between possibilities. A photon's final appearance can depend on paths that were separated and reunited, on rhythms that either cooperate or oppose, on tiny differences that become visible only when everything is brought back together. So when you hear that light can be split, rejoined, and made to vanish, the most important part is not the vanishing itself. The most important part is what the vanishing reveals. It shows that reality can be controlled not only by blocking, pushing, or touching, but by arranging. The same light, guided differently, produces a different world at the detector. One arrangement gives brightness, another gives darkness. Nothing has been cheated. Nothing has been lost. The universe has simply redirected the outcome through interference, and perhaps that is why the idea stays with you. Light is the symbol of clarity. We use it as a metaphor for truth, understanding, discovery. To bring something into the light means to reveal it. But here, light reveals something by disappearing. It teaches that clarity is not always brightness. Sometimes the deepest information is hidden inside a carefully shaped dark place. Sometimes absence is not a lack, but a pattern. Sometimes the proof that something happened is not a flash on the screen, but the exact place where no flash appears. The next time you see sunlight crossing a quiet room, it may seem simple again. In one sense, it is. Light travels, reflects, warms, and illuminates. But behind that everyday softness is a deeper rhythm. The same light that fills a room can be divided into paths, reunited with itself, and made to vanish from one direction, because its own wave-like nature returns in perfect opposition. Nothing mystical has occurred. Nothing has broken the rules. The rules themselves are stranger than intuition. Even light, the thing we trust to show us the world, carries a hidden language of timing and cancellation. And sometimes, the clearest sign that light was there is the darkness it leaves behind. The absence of a click can still be information. A machine that seems to do nothing can still tell the truth if the silence was arranged carefully enough. Imagine a dark laboratory where a tiny detector waits in perfect stillness, built for one simple purpose: to notice the arrival of a photon. A photon is a particle of light, so small that when it is detected, it does not appear as a smooth glow. It appears as an event, a pulse, a Mach, a click. In ordinary life, a click means something happened, and no click means nothing happened. That feels obvious. A doorbell rings, someone is there. It stays silent, and maybe no one came. But quantum physics asks us to be more careful. In a well-designed experiment, no click does not always mean ignorance. It can mean the detector was ready, the timing was known, the path was open, the event was possible, and yet the event did not occur. And from that missing signal, scientists can learn something real. This is why physicists sometimes speak of click and no-click records. A click gives one kind of answer. A no-click gives another. The important part is not the silence by itself, but the conditions around it. A detector that is turned off tells you nothing. A broken detector tells you nothing. A detector placed in the wrong place may only confuse the story. But if a working detector is placed exactly where a photon should arrive under certain conditions, and it remains quiet during the right window of time, then that quiet result becomes part of the experiment. It can rule out one possibility and make another more likely. In that sense, the detector has not failed to speak. It has answered in the only way the setup allowed it to answer. To understand this gently, imagine you are trying to learn whether a tiny quantum system has changed state. If it changes, it should release a photon. If it does not change, no photon should appear. You place a detector nearby and wait. If the detector clicks, you know the system emitted light. If it does not click, you may learn that the system remained where it was, or that it entered a condition where no light was produced. The result is not dramatic, but it is meaningful. The absence of a signal has reduced uncertainty. It has changed what you can honestly say about the system. Real experiments must treat this carefully. No-click information is powerful only when scientists account for detector efficiency, background noise, timing errors, missed photons, and false signals known as dark counts. This is what keeps the idea from becoming mystical. Quantum physics is not saying that every blank screen hides a secret. It is saying something much more precise. When an experiment is built so that a signal should appear if one condition is true, then the absence of that signal can become evidence against that condition. Nothing magical is happening. The meaning comes from the design. One of the clearest examples comes from trapped atoms and ions. In certain experiments, scientists hold a single atom or ion in place and shine laser light on it. If the particle is in one internal state, it scatters light again and again, and the detector records a steady pattern of tiny flashes. The atom appears bright, almost like a microscopic lighthouse, but if it moves into another internal state, it stops scattering that light. The flashes disappear, the detector no longer clicks, and that dark period tells scientists that the atom has changed state. This helped make quantum jumps visible in the laboratory. The word jump can sound strange because we often imagine change as smooth and continuous. But in these experiments, the record can show sudden transitions, bright periods, then dark periods, then brightness again. The atom does not show its hidden state by holding up a label. It reveals itself through the pattern of light it gives or withholds. When the clicks stop, the silence is not empty. It is the sign that the atom has entered a different condition. This example makes the idea easier to feel. You are not learning from a vague absence. You are watching a physical system where light should appear if the atom is in one state. And when that light stops appearing, the missing clicks point to another state. It is like watching a lighthouse in fog. If the beam sweeps past again and again, you know it is active. If the beam suddenly vanishes while your instruments are still working, that disappearance becomes part of the message. In quantum physics, the message may be written not only in flashes, but in the spaces between them. No-click information also appears in quantum communication and quantum computing experiments. In these fields, scientists often care not only about whether a detector fires, but about the full pattern of results. A click here, no click there, a delay, a missing photon, a quiet interval. Together, these details form a map of what happened inside the experiment. Sometimes success is confirmed by a signal appearing in one place. Sometimes it is confirmed by a signal failing to appear somewhere else, because that missing signal rules out an unwanted error or a wrong path. This matters because information is not the same as noise. Information is a reduction of uncertainty. If a no-click result removes one possible explanation, then it has done real work. It has helped shape the story. In quantum physics, this can go even deeper, because a system is often described by multiple possible outcomes before measurement. A click can select one direction for the system's description. A sustained no-click record can guide it another way. Physicists describe this kind of evolution using ideas such as quantum trajectories, where the system's path is conditioned by the measurement record over time. The quiet parts of that record are still part of the record. This can feel almost alive, as if reality is made not only from events, but also from events that were allowed to happen and did not. But the idea is not mystical. It is careful, repeatable physics. The detector matters because it was physically connected to the possible outcome. It was not an empty witness. It was part of the question. If the system had behaved one way, the detector could have clicked. Since it did not, the remaining possibilities change. There is a calm beauty in this. Quantum physics is often introduced through dramatic images. Particles in two places, cats both alive and dead, light acting like a wave and a particle. But some of its strangest lessons are quieter. Sometimes the most important result is not a flash, but the end of flashing. Not a collision, but the absence of one. Not a loud signal, but a carefully measured silence. A detector waits in darkness, and from that darkness, scientists may learn the state of an atom, the absence of an emission, the survival of a fragile quantum condition, or the fact that a transition has not occurred. That is why the phrase, "the absence of a click can still be information," is so powerful. It does not mean doing nothing teaches you everything. It means that in the right experimental world, nothing happening can be different from not knowing. The difference is preparation. The detector was ready. The question was clear. The possible answer had a place to appear, and when it did not appear, the missing event became meaningful. In everyday life, we usually trust presence more than absence. We notice the alarm that rings, not the danger that never arrives. We notice the word spoken, not the one held back. We notice the footprint in snow, not the untouched path beside it. But science often teaches us to pay attention to structure, not drama. If every possible walker had only one gate to pass through, then untouched snow near that gate would tell a story too. So when you imagine a quantum detector that does not click, do not picture a useless machine sitting in a meaningless room. Picture a precise experiment where the universe has been given a narrow way to answer yes, and instead it answers no. That no does not end the story. It shapes it. It tells scientists which possibilities have faded, which conditions remain, and which hidden state may now be true. In the smallest silence of a quantum laboratory, reality reveals a strange lesson. The world is not only built from what appears, but also from what carefully, measurably, and meaningfully does not. One photon can build an interference pattern alone. The most unsettling photograph in quantum physics is not a picture of something impossible. It is a picture built from thousands of tiny ordinary dots. Dots that arrive one by one, randomly at first, and yet slowly arrange themselves into waves. Imagine a screen waiting in darkness while a source of light is made so faint that only one photon is released at a time. Not a beam, not a crowd, not a flood of light. Just one photon, then a pause, then another, each traveling alone through the experiment as if it has no companion to guide it, no partner to interfere with, no swarm to help it form a pattern. If light were only a rain of tiny pellets, you would expect each photon to pass through one opening or the other, hit the screen, and gradually build two simple bright bands, like grains of sand collecting behind two narrow gaps. But that is not what happens. At first, the screen looks meaningless. One dot appears here, another appears there, a third lands somewhere else. Nothing about the first few marks seems wave-like. There is no visible stripe, no smooth ripple, no obvious order. It looks like chance scattering itself across a black surface. But if you keep waiting, if the experiment repeats again and again under the same careful conditions, the dots begin to reveal something hidden. Bright bands and dark bands slowly emerge. The final image becomes an interference pattern, the signature of wave behavior, even though the photons were sent through the apparatus one at a time. That is the quiet shock of single-photon interference. One photon does not need another photon to interfere with. The pattern is not created because photons bump into each other, communicate with each other, or organize themselves like a crowd. Each photon arrives as a single event, a sharp mark on the screen, but the probability of where that mark appears is shaped by a wave-like structure. The photon is detected like a particle, yet its possible journey is described by something spread out, something that can involve more than one path before the final dot appears. This is where ordinary intuition begins to fail, because we are used to choosing between simple categories. A thing is either a particle, like a tiny bead, or a wave, like a ripple on water. But light refuses to live inside either picture completely. It does not behave like a little glowing marble flying through one obvious route. and it does not behave like an ordinary ocean wave that spreads out and deposits energy everywhere at once. It gives you one dot at a time, but many dots reveal a wave-like law underneath. When both slits are open, the photon's possible behavior is shaped by both openings. Close one slit and the pattern changes. Open both and the interference returns. This does not mean a single photon paints the whole pattern in one heroic journey. It leaves only one mark, but the place where that mark is likely to appear depends on the entire experimental arrangement. The photon belongs to the setup, the source, the slits, the distance to the screen, the alignment, the repeated preparation of the same conditions. Change the stage and the outcome changes. That is not mystical. It is not a claim that the photon thinks, chooses, or knows what you are doing. It is a precise feature of quantum behavior. The probabilities depend on the physical possibilities available to the quantum object. This is one of the deepest lessons of the experiment. A single photon landing on the screen does not show you the whole truth. It gives you one result, one mark, one tiny piece of the answer. But repeat the same experiment patiently, and the hidden rhythm appears. At this scale, nature usually does not promise the exact location of the next event. Quantum theory may not tell you precisely where the next photon will land, but it can tell you with extraordinary accuracy how the full pattern will form after many trials. The universe does not hand you certainty one photon at a time. It hands you probability, then lets patience reveal the shape. That is why the image feels so powerful. In the beginning, the dots look random. In the middle, they begin to hint at order. By the end, you realize the pattern was never painted all at once. It was built slowly from individual arrivals, each one unpredictable in detail, yet governed by a deeper rule. The interference pattern was not visible as an object moving through space. It was present as a structure of likelihood, guiding where events could gather and where they almost never would. The dark bands are just as important as the bright ones, because they show where photons rarely arrive. They are not empty by accident. They are shaped absences, carved by interference. For centuries, people tried to decide what light really was. Newton's picture made it feel particle-like. Later wave theories explained reflection, diffraction, and interference with beautiful clarity. Then quantum experiments forced both images into the same room. A photon is not simply a particle in the old sense, and it is not simply a wave in the everyday sense. It is a quantum object. The words particle and wave are useful, but they are not cages. When light is detected, it appears in discrete packets. When its possible paths are allowed to overlap, it produces interference. The strangeness is not that light changes costumes to confuse us. The strangeness is that our familiar categories were never large enough. And this is what makes the single-photon version so important. If you send many photons at once, someone might imagine they are somehow interacting with each other and creating the pattern together. But when the light is dimmed, so that only one photon passes through the apparatus at a time, that explanation disappears. The effect remains. One photon contributes one dot, but the distribution of many dots still follows the interference law. The wave-like behavior is not just a crowd effect. It belongs to the quantum description of each individual photon. The experiment becomes a doorway into a stranger kind of reality, where a single event is local, but the rule behind it is spread across possibilities. This does not make quantum physics helpless or vague. In fact, it is one of the most successful theories ever created. Its predictions are not weak guesses. They are precise patterns. The uncertainty is not a failure of the theory. It is part of what the theory says the world is like at that scale. You may not receive certainty in the next dot, but you receive astonishing accuracy in the final image. That is a different kind of knowledge. Less like predicting the exact fall of a single raindrop, and more like knowing the shape of the storm. There is something almost gentle about this experiment, even though its meaning is profound. Quantum weirdness is often described with loud examples. Cats both alive and dead, particles in two places, futures seeming to affect the past. But here the strangeness arrives quietly. A dot appears, then another, then another. Nothing dramatic happens at first. No explosion, no flash of impossible color, no visible wave washing across the screen. Only patience turns the mystery into an image. The experiment asks you not to judge reality from the first mark. It asks you to wait long enough for the hidden order to show itself. And perhaps that is why the final interference pattern stays in the mind. It is not just a scientific result. It is a picture of how different quantum reality is from ordinary expectation. You look at the screen and see a pattern made by solitary arrivals, each one small enough to seem meaningless on its own, each one necessary for the whole. The photon never draws the full image in a single motion. It simply lands, then the experiment repeats, and slowly, what looked like randomness becomes architecture. So when you hear that one photon can build an interference pattern alone, do not imagine a single particle sketching bright and dark stripes by itself. Imagine something subtler, a lone quantum event repeated under the same conditions, each arrival uncertain, yet guided by a wave-like rule that becomes visible only through accumulation. A photon is detected as one dot, but its probabilities carry the memory of the arrangement. The screen receives individual marks, but the experiment reveals a pattern. And in that slow gathering of light, quantum physics teaches one of its deepest lessons. Reality is not always found in the single moment you can point to. Sometimes it is found in the shape that appears only after the universe has answered the same question again and again. A detector can destroy a pattern without touching the screen. A pattern can disappear from a screen even when nothing touches the screen at all. That is the first strange thing to understand. Imagine a dark laboratory where tiny particles are passing through two narrow openings and landing on a distant surface one by one. At first the marks seem random. Then, slowly, as more particles arrive, something delicate begins to appear. Bright bands and dark bands, a wave-like interference pattern forming from countless individual impacts. The screen has not moved. The slits remain open. The source continues to send particles forward. Everything seems the same. But now place a detector near the paths, before the particles reach the screen. A detector whose only job is to learn which slit each particle could have passed through. It does not wipe the screen. It does not block the final surface. It does not erase the marks after they land. And yet the pattern fades. The soft bands vanish. What remains is no longer the strange fingerprint of interference, but a simpler spread of impacts, the kind you would expect from particles behaving as if each one took a definite route. This is one of the deepest lessons of quantum measurement. The final image can be changed before the particle ever reaches the place where the image appears. In the double-slit experiment, interference depends on a very fragile condition. The possible paths must remain indistinguishable. If no information exists about which slit the particle went through, the quantum description can include both alternatives at once. Those alternatives can overlap, combine, and shape the probabilities of where the particle may land. Over many arrivals, the screen reveals that hidden structure as bright and dark bands. But when a detector is added near the slits, the situation changes. The particle's route becomes linked to a physical record, even if no human being looks at that record right away. Even if the detector sits quietly in the apparatus, the information has still become available in the world. The paths are no longer cleanly interchangeable. One possibility has left one trace, the other possibility has left another, and once the alternatives can be told apart, they can no longer interfere in the same way. This does not happen because consciousness magically forces the particle to behave. It is not human curiosity frightening the quantum world into obedience. The reason is more precise. Interference requires ambiguity between alternatives. The moment the experiment creates reliable which-path information, the wave-like relationship between the paths is weakened or lost. A detector does not need to be violent to change the outcome. It only needs to mark the route. It only needs to carry a difference. In quantum physics, that difference matters. A tiny physical record, even one hidden in the detector or scattered into the environment, can be enough to destroy the fragile overlap that interference needs. Think of two identical whispers, entering a silent room from different directions. If nothing distinguishes them, they can blend into one strange shared sound. But if each whisper leaves a different echo, a different label, a different signature, the blending is no longer the same. The sound has not been struck at the place where you hear it. The wall has not been damaged. But the relationship between the whispers has changed before they reach you. In the quantum experiment, the detector creates that kind of label. It turns two indistinguishable possibilities into two knowable alternatives. And when the roots become knowable, the interference pattern loses the very condition that allowed it to exist. This is why the screen is only the final page of the story. It records the outcome, but it does not contain the whole cause. The pattern depends on the source, the slits, the distance, the alignment, the surrounding environment, and whether the particle's possible routes remain unmarked. If the paths stay indistinguishable, interference can appear. If the paths become distinguishable, the pattern fades. The marks still arrive, the particles still hit the screen, but the hidden rhythm that once guided those marks into bands has been broken. This effect has been shown in many forms, not only with photons but also with electrons, atoms, and even larger molecules under carefully controlled conditions. The rule remains beautifully consistent. The more clearly the path can be known, the weaker the interference becomes. The more completely the path information is erased or unavailable, the more the interference can return. This is part of what physicists call complementarity. You cannot have full witch path knowledge and full interference visibility in the same arrangement. It is not merely a problem of bad instruments or blurry cameras. It is not that scientists are too clumsy to measure both at once. It is a feature of quantum reality itself. The experiment can be arranged to reveal path-like behavior, or it can be arranged to preserve wave-like interference, but it cannot fully reveal both in the same way at the same time. Decoherence helps explain why this is so important. In everyday life, quantum interference is usually hidden because objects are constantly interacting with their surroundings. Air molecules, stray light, heat, vibrations, and countless tiny environmental traces are always carrying information away. These interactions act like uncontrolled detectors. They mark possibilities. They leak information into the world. A laboratory detector is simply a cleaner, more deliberate version of that process. It shows us what the environment is doing all the time, turning delicate quantum possibilities into distinguishable histories. The quantum world does not need a dramatic collision to lose its strangeness. Sometimes all it takes is a trace. That is what makes this idea so unsettling. We usually think of information as harmless. To learn something seems passive, almost weightless. You look, you discover, and the world remains as it was. But quantum physics tells a different story. Information is not always just a mirror held up to reality. Sometimes it is part of the machinery that decides which patterns can exist. A detector does not merely reveal a route. By creating a record of that route, it changes the relationship between the alternatives. It draws a boundary where ambiguity once lived. The screen, then, is showing you the aftermath of a deeper change. The interference does not die because the screen is touched. It dies because the possible paths have stopped being able to meet as indistinguishable possibilities. The detector has added memory to the experiment, and in quantum physics, memory is not neutral. A record, even a tiny one, can be enough to turn a wave-like pattern of possibilities into a more particle-like distribution of outcomes. This is why the experiment feels almost philosophical while remaining completely physical. It suggests that the visible world is not always shaped at the place where we finally see the result. Sometimes the outcome is shaped earlier, in the hidden conditions that decide whether possibilities remain open and blended or become separated and labeled. A detector near the slit does not need to shout. It only needs to remember. That memory can live in a device, in scattered light, in a slight change of the environment, or in any physical trace that makes one path different from the other. Once the world has a way to know which route was taken, the old interference can no longer form. So when you picture this experiment, do not imagine someone erasing stripes from a screen like chalk from a board. Imagine something subtler, a pattern that depends on uncertainty, a set of possible paths that must remain unmarked, and a detector quietly attaching a label before the final image has a chance to appear. The particles still arrive. The marks still collect, but the music between the paths has gone silent. What disappears is not the particles themselves, but the relationship that once allowed their probabilities to form waves. And that is the strange lesson at the heart of it. Reality does not always change because something is struck where you are looking. Sometimes it changes because somewhere earlier, somewhere quieter, the world has learned too much. The screen remains untouched, but the possibilities are no longer free to overlap. The final pattern fades not from damage, not from force, not from a hand reaching toward the surface, but from information entering the experiment. In quantum physics, a detector can destroy a pattern without touching the screen, because the pattern was never only on the screen. It was in the fragile agreement between paths, and once those paths become known, the agreement is gone. A particle can leave evidence of paths it never took. A particle can seem to leave a whisper in a place where it never walked, and that is where the old picture of motion begins to lose its power. Imagine a photon entering a quiet maze of mirrors, not a messy maze with rough corners and visible corridors, but a perfectly balanced optical maze where every path is polished, every reflection is timed, and every tiny disturbance can leave a trace. In the ordinary world, the question, "Where was it?" feels simple. A car was on this road or that road. A bird was on the branch or in the sky. A person entered the room or stayed outside. We expect the past to behave like a line of footprints. One step after another, connected, continuous, easy to draw. But quantum physics does not always give the past back to us in that familiar shape. Sometimes a particle's history is not like footprints in wet ground. Sometimes it is more like an echo moving through a building, carrying hints from rooms that do not fit the route you thought it must have taken. One of the most provocative versions of this idea comes from experiments inspired by a strange question. Where have photons been? In a nested Mach Zehnder interferometer, light is guided through an outer interferometer that contains a smaller interferometer inside it. So instead of a simple left or right choice, the photon's possible history is arranged like a maze inside a maze. In a famous 2013 experiment by Darnan and colleagues, tiny mirrors along different paths were made to vibrate at different frequencies, almost as if each path was given its own quiet musical note. These vibrations were extremely gentle. They were not meant to grab the photon, stop it, or force it into one ordinary route. They were weak enough to preserve much of the quantum behavior, but strong enough that if the photon left a faint trace in a certain region, that trace could later appear in the final signal, and then came the unsettling part. The detected photons seemed to carry signs from some internal paths of the interferometer, while not carrying the signs you would expect from the entry and exit paths connected to them. In simple language, the photon appeared to leave evidence in places that did not form a normal continuous route. It was as if the final signal contained echoes from rooms inside the maze, but not from the hallway that should have led into or out of them. That is why the result became famous and also controversial. It seemed to challenge the comforting idea that a particle's past must always be a clean line drawn through space. But this is where the story must stay honest. The experiment does not prove that a tiny glowing bead secretly teleported into impossible corridors. It does not mean the photon became a ghost, cheated the maze, or wandered through places in the way a tiny marble would. The real lesson is subtler and more interesting. When quantum systems are studied with very delicate methods, the answer to "where was it?" may not look like one simple path. It may look like a pattern of traces, correlations, and conditions that only make sense inside the full experiment. This is where weak measurement becomes important. A weak measurement is a very gentle kind of measurement. Instead of strongly forcing the particle to give one clear answer, it gathers only a tiny hint from each trial. One weak measurement by itself usually tells you very little, almost like hearing one faint note in the distance. But repeat the experiment many times and a pattern can appear. Post-selection adds another layer. After all the photons are detected, scientists only study the cases that ended in a particular final result. So the experiment is not like placing a security camera in the maze and watching exactly where one photon went. It is more like asking a very delicate question, many times, and then looking only at the answers that ended in a chosen way. That is why the interpretation matters. Some physicists argue that these weak traces tell us something meaningful about where the photon was, in a quantum sense. Others argue that the same signals can be explained through standard wave behavior inside the interferometer, and that saying the photon had a discontinuous past may be misleading. This disagreement is not a failure of the science. It is part of what makes the experiment so valuable. It shows that quantum physics is not only strange because the answers are strange. It is strange because even our questions may carry assumptions that are too simple. Which path did it take? Sounds like a natural question. But hidden inside that question is an old picture. The idea that a particle must move like a tiny stone, following one connected route whether we see it or not. The nested interferometer challenges that picture. It suggests that in certain quantum situations, asking for the particle's past may not be the same as asking for a road on a map. The final signal can depend on preparation, interference, weak traces, and the particular outcome selected at the end. The photon's history is not handed to us as a simple travel diary. It comes as a structure. In everyday life, evidence usually means contact. Mud on your shoes means you stepped in mud. A fingerprint on glass means a finger touched the glass. A footprint in snow means someone passed there. But quantum evidence can be more relational. It can depend on how possibilities overlap, which alternatives cancel, which traces survive, and how the final measurement filters the story. So when a particle seems to leave evidence of paths it never took, the evidence is not a footprint from a tiny object marching through a corridor. It is a weak mark inside the structure of possibility itself. Think of a melody played inside a strange building. You stand at the exit and hear a note that seems to carry the character of a room no person could have entered directly. At first, it feels impossible, but if the walls, doors, echoes, and resonances are arranged in just the right way, the final sound can still contain that room's signature. The sound is not lying. Your simple map of the building is incomplete. Quantum particles are like that. They do not always describe their past as a neat sequence of locations. Sometimes they reveal it as an echo of the entire arrangement. This is where the experiment becomes quietly philosophical, without leaving science behind. It asks whether the past of a quantum particle is always a sequence of definite positions, or whether past can depend on how the system was prepared, how it was later detected, and what kind of question was asked in between. That does not mean the past can be rewritten however we like. It does not mean consciousness controls the photon. It does not mean particles are mischievous, supernatural, or aware. It means the classical idea of a path may not be the right language for every quantum situation. And that is the humbling part. Our idea of motion was built from large things: stones, bodies, animals, planets, cars, falling leaves. These things appear to move along continuous roads because they are constantly interacting with the world around them, leaving records everywhere. But a single quantum object lives under quieter rules. It can be prepared in a state where several alternatives matter. It can be measured so gently that only faint traces are collected. It can be selected afterward according to a final outcome. And when all of that is put together, the answer to where was it may no longer resemble a trail you can draw with one unbroken line. So the real lesson is not that photons break reality. The lesson is that our everyday language breaks down when we try to force quantum reality into it. A photon can arrive at a detector with traces that do not form a clean route, not because nature is confused, but because our expectation was too narrow. We wanted a road. The experiment gave us an echo. We wanted a continuous trail. The quantum world gave us a pattern of weak marks, filtered outcomes, and overlapping possibilities. This is why the idea stays with you. It changes the meaning of a simple question. Where was the particle? No longer feels innocent. It becomes a question about what kind of measurement was used, what final result was selected, and whether the word where still means what it means in ordinary life. Quantum measurement is not always about uncovering a hidden little path waiting under the surface. Sometimes it is about discovering which questions nature can answer cleanly, which questions it can answer only faintly, and which questions fall apart because they were too human from the beginning. So when you hear that a particle can leave evidence of paths it never took, do not imagine a ghost wandering impossible corridors. Imagine a delicate optical maze where every mirror gives possibility a voice. Every weak trace is a soft mark, and the final signal arrives like an echo from a past that cannot be drawn as one continuous road. The photon has not betrayed reality. It has betrayed only our expectation that reality must always travel by roads. Some experiments feel like reality is answering questions. Reality does not always behave like a book waiting to be read. Sometimes it behaves more like a quiet witness that only answers the exact question your experiment is built to ask. Imagine walking into a room where the walls are covered with sealed envelopes, but each envelope can only be opened by a different kind of key. One key does not reveal the whole truth. It reveals only the message written for that key. Turn the key one way, and the room answers in one language. Turn it another way, and the answer changes. Not because the room is lying, but because you have asked a different question. This is one of the most quietly powerful ideas in quantum physics. Experiments are not just windows looking at a fixed hidden world. They are carefully shaped questions posed to nature. A detector, a filter, a magnetic field, a mirror, a timing device. Each one does more than look. It defines what kind of answer can appear. In daily life, this feels strange because we assume properties are already sitting inside objects, waiting to be discovered. A coin is heads or tails before you look. A book has a certain number of pages before you count them. A stone has weight, position, shape, and temperature whether you measure them or not. But quantum systems do not always offer that kind of pre-written completeness. A photon's polarization, an electron's spin, an atom's energy. These can behave as if their answer depends on the measurement context, on the exact question being asked. Take polarized light as a gentle example. A photon can pass through a polarizing filter depending on how its polarization relates to the filter's direction. If the filter is vertical, the experiment is asking one kind of yes or no question. Are you aligned with this direction? If the filter is tilted, the question changes. The photon is not simply carrying a little label that answers every possible filter direction at once in the way a tiny classical arrow might. Quantum theory tells us how likely each answer is, and the experiment gives one actual result. That result is real, but it is tied to the question. This is why some quantum experiments feel almost conversational. Not because nature has a mind, not because particles understand your intention, not because reality is magical, but because the measuring setup selects which feature of the system can become definite. The apparatus is the grammar of the question, and the result is the sentence nature is allowed to speak. This becomes even clearer when scientists measure something like spin, a quantum property with no perfect everyday equivalent. If you measure an electron's spin along one direction, you get one of two possible answers. If you measure along a different direction, you are asking a different question, and the earlier answer may no longer behave like a stable fact for the new direction. The old instinct says, surely the electron had all those answers hidden inside it already. But quantum experiments resist that idea. They suggest that some properties are not like coins in pockets. They are more like responses produced in a meeting between the system and the measuring arrangement. The answer is not fake. The outcome is recorded. The detector clicks, the screen marks, the lab notebook receives a number, but the meaning of that number belongs to the question that produced it. This is why physicist John Wheeler liked to speak of a participatory universe. Though the phrase must be handled carefully, it does not mean human thoughts control the cosmos. It means observation in physics is an active physical process, and the design of the experiment helps define which aspect of reality becomes visible. You do not stand outside nature like a ghost looking through glass. Your instruments are made of nature too. Your question enters the world through matter, light, magnets, electronics, and timing. The experiment is part of the event. That is a humbling shift. It means science is not simply collecting answers from a silent warehouse of facts. It is learning how to ask better questions, cleaner questions, questions that do not confuse the answer by demanding too much at once, and quantum physics is strict about that. Some questions cannot be asked together with unlimited sharpness. Some measurements disturb the possibility of others. Some arrangements reveal wave-like behavior, while others reveal particle-like behavior. Some setups show interference, while others reveal path information. The world does not hand over every face at the same time. It turns toward the instrument you build. This can feel frustrating at first, as if nature is evasive, but it may also be one of the most honest lessons science has ever given us. The answers we get depend on the questions we are capable of forming. A blurry question gives a blurry truth. A precise question gives a precise truth, but only along the narrow path that question opens. In that sense, quantum experiments train the mind to become less arrogant. They remind you that knowing is not the same as possessing reality completely. Knowing is an interaction. It is a relationship. It is a careful exchange between what is out there and what you are prepared to ask. And this is where the topic becomes quietly philosophical, without leaving the ground of real physics. You begin to wonder how much of life works this way too. Not in the literal quantum sense, but in the softer human sense, that the questions you ask shape the world you notice. Ask only what can go wrong, and reality seems to answer with threats. Ask only what can be controlled, and mystery disappears behind machinery. Ask what can be learned, and even confusion becomes a teacher. The universe of daily experience is not a laboratory photon, but your attention still acts like a kind of filter. It selects, it frames, it invites certain answers and leaves others in shadow. Quantum physics does not prove that thoughts create reality in the simple way people sometimes claim, but it does show something more disciplined and more beautiful. The form of inquiry matters. The way you measure shapes what can be known. The question is never neutral. In a quantum lab, a piece of equipment may be asking, which state are you in? Or which direction are you aligned with? Or which outcome can be registered here? And nature responds with one allowed result. Not always the one you expect, but always within the rules. That is why some experiments feel like reality is answering questions. The feeling comes from the strange precision of the exchange. You change the question, the pattern of possible answers changes. You refine the apparatus, the response becomes clearer. You ask the wrong question, and nature refuses to give the kind of answer your intuition wanted. In the end, the deepest lesson may be this: reality is not mute, but it is not careless with its answers. It speaks through experiments, through constraints, through probabilities becoming events, through instruments that turn invisible possibilities into visible marks. And if you listen closely, the quantum world seems to say that truth is not simply found by staring harder. It is found by learning how to ask. A mirror can decide whether light acts like a wave. A single mirror placed or removed at the last possible moment can make light seem to change its mind about what it has always been. Picture a photon entering a quiet interferometer, a device made from mirrors and beam splitters that guides light along two possible routes before sending it toward detectors. At the beginning, the photon meets the first beam splitter, which gives the experiment two possible paths to work with. If the second beam splitter, the final mirror-like element that recombines those paths, is present, the two possibilities meet again before detection, and the setup can reveal wave-like behavior through interference. One detector may become favored, the other suppressed, not because light has been destroyed, but because the possible routes have been brought together in a way that allows them to reinforce or cancel. But if that second beam splitter is absent, the paths are not recombined. Each detector corresponds more directly to one route, and the result looks particle-like, as though the photon traveled one path rather than behaving as a spread-out wave of possibility. This is the heart of Wheeler's delayed choice idea. The choice of whether to observe wave-like interference or particle-like path behavior can be made after the photon has already entered the apparatus, as if the experiment waits until the last stage to decide which face of light will become visible. In a Mach Zehnder interferometer, adding the second beam splitter gives each detector two possible ways to receive the photon and creates the conditions for interference. Without it, the detectors instead provide which path style information. That is why the title sounds so impossible. A mirror can decide whether light acts like a wave, but the honest version is more subtle. The mirror does not command the photon like a judge giving orders. It does not reach backward with magic. It does not prove that light was first one thing, then suddenly became another thing because a human changed their mind. What it shows is that the behavior we call wave or particle is not a costume light secretly wears in isolation. It is a feature revealed by the whole measurement arrangement. Change the arrangement, and you change the kind of answer nature can give. If the final beam splitter is in place, the experiment asks, can the possible paths interfere? If it is removed, the experiment asks, which path can be associated with the detection? The photon does not need to carry a tiny passport stamped wave or particle before the question is asked. Quantum physics refuses that simple image. It says the outcome belongs to the relationship between the photon and the apparatus, between the possible paths and the way they are finally tested. Wheeler emphasized that delaying the choice of measurement arrangement does not change the observable predictions. What matters is the definite experimental setup used to obtain the result. This is why the experiment is so powerful for the mind. It does not merely show that light is strange. It shows that some properties are not revealed in the same way as ordinary hidden facts. If you place a coin under a cup, the coin is already heads or tails, whether you look now or later. But a photon in this kind of experiment is not just a tiny coin under a cosmic cup. When its possible paths remain available for recombination, interference can appear. When the paths are separated into distinguishable alternatives, the interference disappears. The mirror's role is not decorative. It decides whether the paths can meet as possibilities or remain separated as routes. And the delayed choice version makes the idea sharper. The decision to include or exclude that final recombining element can be postponed until after the photon has passed the first beam splitter. So the old question, did it travel as a wave or as a particle, begins to feel like the wrong question. It is more accurate to say that the experiment determines which aspect can be observed. Recent delayed choice and quantum delayed choice experiments continue to test this complementarity, showing that a simple classical picture of light as only a wave or only a particle is inadequate. There is something almost theatrical about this, but the theatre is built from real optics. The first beam splitter opens a fork in the story. The mirrors guide the alternatives. The second beam splitter decides whether those alternatives are compared. The detectors record the final answer, yet no single piece alone contains the whole meaning. The meaning lives in the arrangement. And this is one of the deepest habits quantum physics forces you to break. The habit of imagining reality as a collection of objects carrying complete answers everywhere they go. In these experiments, the answer is not simply carried. It is produced through the way the question is physically asked. The photon is detected as one event, one click, one arrival. But the probabilities leading to that arrival depend on whether the apparatus allowed interference or path distinction. A mirror then becomes more than a reflecting surface. It becomes a boundary between two kinds of knowledge. With it, you see the wave-like side of light's behavior. Without it, you preserve the path-like story. And you cannot demand both with full clarity from the same arrangement. That is not because the equipment is clumsy. It is because complementarity is woven into the rules. The more completely the experiment is arranged to reveal one face, the more it hides the other. And perhaps this is the quiet emotional pull of the subject. It reminds you that truth may not always be a single object sitting in the dark, waiting for the right lamp. Sometimes truth is conditional, not in the sense of being fake, but in the sense of being relational. What you learn depends on what you make it possible to learn. Ask light a path question and it answers like a particle. Ask it an interference question and it answers like a wave. Ask both at once in the old simple way, and the question itself begins to break. So when you imagine that final mirror being inserted or removed, do not picture a photon panicking in midair, trying to decide what identity to wear. Picture a more delicate reality, a quantum object entering a world of possible tests, while the final arrangement determines which pattern can become real in the detector record. The photon is not changing its mind. Your experiment is changing its question, and in the quiet click that follows, light answers exactly the question the mirror allowed you to ask. Two photons can refuse to leave separately. Two particles of light can meet at a half-silvered mirror and leave as though separation has become forbidden. Imagine two photons approaching the same beam splitter from opposite sides, timed so perfectly that they arrive together, carrying the same color, the same polarization, the same shape, the same rhythm, so that no hidden label in the universe can tell one from the other. In ordinary thinking, you would expect several simple outcomes. Maybe both photons pass through. Maybe both reflect. Maybe one goes one way and the other goes the other way. If they were tiny classical beads, half the time you would expect them to separate after the meeting, each leaving by a different exit. But in the quantum world, when the photons are truly indistinguishable and arrive together at a balanced beam splitter, the separate exit outcome disappears. The two photons leave together through the same output. Not always the same output, but together. Sometimes both go left, sometimes both go right. What they seem to refuse is leaving separately. This is the Hong-O-Mandel effect, first demonstrated in 1987, and it remains one of the cleanest demonstrations that quantum objects do not behave like little independent marbles when their identities cannot be told apart. In a typical HOM experiment, scientists place one detector at each output of the beam splitter and look for coincidence counts, meaning moments when both detectors click at the same time. If the photons are distinguishable, perhaps because one arrives slightly earlier, or has a different wavelength, or a different polarization, coincidences appear as expected. But as the photons are made more and more identical and their arrival times overlap, those coincidences drop. The graph forms a famous dip, a valley in the number of separated detections, showing that the photons are bunching together instead of splitting apart. This reduction of coincidence counts at zero delay is the signature of Hong-O-Mandel interference, and it is widely used to test how indistinguishable two photons really are. The beautiful part is that this is not caused by one photon pushing the other, attracting it, or communicating with it like two tiny travelers making a decision at a crossroads. Photons do not carry little minds. They do not prefer company. The effect comes from quantum interference between alternatives that cannot be physically distinguished. There are two different ways to get one photon in each output. One photon could be transmitted while the other reflects, or the first could reflect while the other transmits. For distinguishable photons, those alternatives can be counted separately. For indistinguishable photons, nature does not keep those alternatives apart. They overlap, and their probability contributions cancel for the case where the photons leave separately. What remains are the two outcomes where both photons leave together through one port or both leave together through the other. This is why the effect feels so strange. The photons are not interfering with themselves in the single-photon sense. The two photon alternatives are interfering with each other. The mystery is not hidden in a bright pattern on a screen, but in the absence of paired clicks from two detectors. The missing coincidences are the evidence. The dip is the footprint of indistinguishability, and because the effect depends so sharply on sameness, it becomes an extraordinary scientific tool. By sliding one photon's path by an almost impossibly tiny amount, researchers can see the dip deepen or disappear, using the photons themselves as a ruler for timing differences far below what ordinary electronics could easily resolve. The original homework was connected to measuring extremely small time intervals between photons, and modern SHOM interferometry remains a standard method for testing single-photon sources and comparing quantum states. In quantum technologies, this matters deeply. If you want to build optical quantum computers, quantum networks, or secure quantum communication systems, You often need photons from different sources to behave as identical carriers of quantum information. If they are too different, the interference weakens. If they match well, the home dip becomes deeper. In that sense, the beam splitter becomes almost like a truth test for sameness. Two photons enter, and the experiment asks a quiet question. Can the universe tell you apart? If the answer is yes, they behave more like separate visitors. If the answer is no, the separate exit story cancels itself, and the photons leave as a pair. This does not mean they fuse into one object. Two photons still exist. Energy is still conserved. Detectors can still register two photons arriving together, but their joint behavior cannot be reduced to two independent stories. They must be described as a shared two-photon quantum state. That is the lesson hiding inside the title. Two photons can refuse to leave separately is not a literal act of refusal. It is a sign that individuality itself has limits in quantum physics. When two particles are truly indistinguishable, asking which one did what can become meaningless, not merely unknown. There may be no fact of the matter that one photon was transmitted and the other reflected. The alternatives dissolve into a combined outcome, and the final behavior belongs to the pair. This is hard to feel because human life is built around labels. You have your face, your memories, your body, your name. You are used to things staying themselves. But photons in the Hom effect teach a quieter rule. In the quantum world, identity is not always a private possession. Sometimes it is erased by perfect sameness. Sometimes what matters is not this one and that one, but the pattern created when the distinction between them can no longer be made. And there is something deeply humbling in that. A beam splitter, a small piece of glass, becomes the stage for a lesson about individuality. Two particles approach from different sides, and if they arrive with even the slightest meaningful difference, the world can sort them into separate exits. But if they are matched so completely that no measurement could tell them apart, then separation loses its ordinary authority. The detectors wait for one click here and one click there, and the expected pair of signals fades away. The silence between the two detectors becomes the message. The photons have not broken physics. They have revealed a rule that was always underneath it. When quantum paths become indistinguishable, reality does not simply choose one classical story. It lets the stories interfere, and sometimes the story of separation cancels out. So when you imagine two photons meeting at a beam splitter, do not picture two glowing grains bouncing like balls. Picture two possibilities becoming so perfectly overlapped that the universe no longer tracks which photon is which, and because it cannot tell them apart, it refuses to write the ending where they leave alone. Quantum teleportation. Transfers. States, not matter. Teleportation in quantum physics is not a body vanishing from one room and appearing in another, but a far stranger kind of transfer. The movement of an invisible condition from one system to another, while the original is erased. Imagine holding a sealed glass lamp whose flame has a shape unlike any other flame, a fragile pattern of heat, color, and motion that cannot be copied by ordinary inspection, because the moment you try to measure every detail, you disturb it. Now imagine that somewhere far away, there is an empty lamp waiting, and through a carefully prepared connection, the exact living pattern of the first flame can be recreated inside the distant lamp, while the first flame loses its original form. Nothing physical flew across the room as a glowing object. The glass did not travel. The fuel did not travel. What moved was the state, the delicate recipe of how that quantum system was arranged. That is the heart of quantum teleportation. It does not transport matter like science fiction. It does not beam a person across space. It does not break the speed of light. It transfers quantum information, the fragile identity of a particle's state, from one particle to another, using a combination of entanglement, measurement, and an ordinary classical message. The idea was proposed in the early 1990s by Charles Bennett and collaborators, and later demonstrated experimentally with photons, showing that a quantum state could be transferred from one system to another without physically carrying the original particle itself. The word teleportation sounds dramatic, almost misleadingly so, because it makes the mind picture bodies dissolving into light. But the real phenomenon is quieter and more precise. In quantum teleportation, the object is not moved. The state is relocated. To understand this gently, picture three particles. One particle carries an unknown quantum state, something you want to transfer but cannot fully read without damaging it. The other two particles are entangled, meaning they share a special quantum connection prepared in advance. One of the entangled particles is kept near the original particle, and the other is sent to the distant receiver. Then, a special joint measurement is performed on the original particle and the nearby entangled particle. This measurement does two things at once. It destroys the original unknown state where it was, and it produces a limited classical result, a small piece of ordinary information that must be sent to the receiver through normal communication, no faster than light. Once the receiver gets that message, they apply a corresponding adjustment to their distant particle, and after that correction, the distant particle carries the original quantum state. The state has been transferred, but the original has not survived as a second copy. This is crucial. Quantum teleportation is not cloning. In fact, quantum mechanics forbids perfect copying of an unknown quantum state, a principle known as the no-cloning theorem. If teleportation allowed perfect duplication, it would break one of the deepest rules of quantum theory. Instead, the process is more like moving a melody from one instrument to another while silencing the first instrument in the act of transfer. The song continues elsewhere, but it is not playing in two places at once. This is one of the reasons quantum teleportation is so scientifically important. It shows that the identity of a quantum object is not tied to its material body in the simple way our intuition expects. If two electrons are identical in every basic property, then what makes one quantum situation different from another is not a tiny label stamped onto the particle, but the state it carries. Teleportation takes that state, that fragile arrangement of possibility, and reconstructs it somewhere else. But it can only work because entanglement has already been shared between the sender and receiver. Entanglement is the hidden bridge, but it is not a usable faster-than-light telephone. The classical message is still required, and until that message arrives, the receiver cannot complete the transformation. This is why quantum teleportation does not violate relativity. No meaningful information can be used instantly across space. The entanglement provides correlations. The classical message tells the receiver how to turn those correlations into the intended state. Without both parts, the teleportation is incomplete. This careful balance is what makes the process so beautiful. It feels almost impossible, yet it obeys the rules with extraordinary discipline. Nothing cheats, nothing outruns light, nothing is copied, the original is consumed, the distant particle is transformed, and the state reappears where matter itself did not travel. In the laboratory, this has been done with photons, atoms, ions, and other quantum systems, and it has become one of the key ideas behind future quantum networks. If quantum computers are ever connected over long distances, they may not send quantum states by simply pushing fragile particles through noisy channels the way ordinary internet data travels through cables. Instead, they may use teleportation-like protocols to move quantum information between nodes, protect delicate states, and link separate quantum devices into larger systems. This matters because quantum states are extremely fragile. Ordinary measurement can ruin them, environmental noise can disturb them, distance can degrade them. Teleportation offers a way to transfer the state without needing the original physical carrier to survive the entire journey. In that sense, it is not a fantasy of disappearing bodies, but a practical method for moving the most delicate kind of information nature allows. And yet, even when explained honestly, the idea still touches something deeply strange. You begin to ask what it means for a thing to be the same thing. If the matter stays behind, but the complete quantum state is recreated elsewhere, what has really moved? For a photon or an atom, this question is scientific. For human beings, it becomes philosophical, and we must be careful not to confuse the two. Quantum teleportation does not mean we can teleport a person. A person is not one simple quantum state waiting to be transferred. A body contains an unimaginable number of particles, constant biological processes, heat, chemistry, memory, consciousness, and environmental interactions. Measuring and transferring all of that is not just technologically difficult, it raises deep physical and conceptual problems far beyond current science. But the real experiment does not need human teleportation to be astonishing. It already teaches something profound at the scale where it truly works. A quantum state can be detached from the specific particle that first carried it and made real in another system. The carrier changes, the pattern survives, and maybe this is why quantum teleportation feels so haunting even when stripped of science fiction. It separates substance from arrangement. It tells you that, at the quantum level, what something is may depend less on the tiny material holder and more on the structure of information it bears. The body of the message does not travel, but the meaning does. The original mark disappears, but the pattern is born again at a distance. And in that quiet exchange, the universe reveals a strange kind of humility. Identity is not always located where matter is. Sometimes it lives in a state, in a relationship, in a fragile description that can be destroyed here and restored there, not by magic, but by entanglement, measurement, and communication working together. So when you hear the phrase quantum teleportation, do not picture a person dissolving into blue light. Picture something smaller, cleaner, and in some ways more mysterious. One quantum system surrendering its unknown state, an entangled pair acting as a prepared bridge, a classical message traveling patiently through space, and a distant particle being adjusted until it becomes the new home of what was lost. Matter has not crossed the gap, but the state has, and sometimes, in the quantum world, that is the part that matters most. Bell tests rule out simple local hidden variables. The universe once offered physicists a bargain that sounded perfectly reasonable. Maybe quantum particles only look mysterious because they are carrying secret instructions we have not learned how to read. Imagine two sealed envelopes created together and sent to opposite sides of the world. When one is opened and says red, the other says blue. There is nothing spooky about that if the answers were written inside from the beginning. You do not need a signal passing between them. You do not need distant influence. You only need hidden information, prepared in advance, traveling quietly with each object. This was the comforting hope behind simple, local, hidden variable ideas. Perhaps quantum randomness is not truly random. Perhaps each particle already carries a private list of answers, and perhaps the world remains local, meaning that what you do here cannot instantly change what is real over there. It is a beautiful hope, because it protects the old intuition that reality has definite properties before measurement, and that distant objects do not coordinate in impossible ways. But then came John Bell, and with one of the most elegant arguments in modern physics, he showed that this comforting picture can be tested. Bell did not simply say quantum mechanics is strange. He asked a sharper question. If particles really carry pre-written local instructions, what limits should their measured correlations obey? In other words, if two distant particles are only connected by information they received in their shared past, then there are boundaries to how strongly their results can match when experimenters choose different measurement settings. These boundaries are called Bell inequalities, though you do not need the mathematics to feel their meaning. They are like rules for any universe where particles have local secret answers already prepared. If experiments stay inside those rules, the old hidden instruction picture might survive. But if experiments break those rules, then simple local hidden variables cannot explain the world. The setup is conceptually gentle, but philosophically explosive. Scientists create pairs of entangled particles, often photons, and send them in opposite directions toward two separate measuring stations. At each station, the experimenter can choose between different measurement settings, like rotating a filter, to ask the photon a slightly different question. Each detector gives a result, then researchers compare many pairs of results from many repeated trials. If each photon merely carried a little hidden answer sheet from the start, the correlations should never exceed Bell's limit. But quantum mechanics predicts stronger correlations, not because the particles send usable messages faster than light, and not because one detector controls the other like a remote switch, but because the pair must be described as a shared quantum system in a way that refuses to fit the old local instruction story. Again and again, Bell-type experiments have found correlations that violate the Bell inequalities, matching quantum predictions and ruling out the simplest dream that particles are just ordinary objects with concealed local properties waiting to be uncovered. This is where the lesson becomes delicate, because it is easy to exaggerate. Bell tests do not mean we can use entanglement to send messages instantly across space. They do not mean every possible hidden variable theory is dead. A hidden variable theory that allows non-local connections, such as Bohmian mechanics, is not ruled out by Bell in the same simple way. Some people also discuss more radical escape routes, such as superdeterminism, where the choices of measurement settings are not truly independent of the particles being measured, though that idea comes with deep conceptual costs. So the honest conclusion is precise. Bell tests rule out simple, local, hidden variable explanations, the kind where measurement outcomes are predetermined by nearby facts, and no distant influence or deeper non-local structure is needed. That precision matters, because the beauty of Bell's work is not in making the wildest possible claim. It is in showing exactly which comfortable assumption nature refuses to obey. The world may still be lawful, it may still be consistent, it may still prevent faster-than-light messaging, but it does not appear to be made from little isolated objects carrying complete local answer sheets. That is the crack Bell opened in reality. Before Bell, the debate between Einstein and quantum mechanics could feel almost philosophical, a disagreement about what the theory meant. Einstein disliked the idea that nature could be truly random, or that distant particles could share a connection too strong for classical locality. He wanted a deeper description, something complete and calm beneath the apparent uncertainty. Bell transformed that debate into an experimental question. He took a question about the soul of physics and placed it on a laboratory table. Then the experiments answered, not with a sentence, not with a grand declaration, but with statistics gathered patiently from pairs of particles, with correlations too strong for the old local hidden story to hold. And if you sit with that long enough, the strange emotional weight of it begins to appear. We often imagine truth as something hidden behind a curtain, waiting for a more powerful light. Bell showed that some curtains cannot hide the kind of world we hoped was there. The issue is not that we lack enough information, like someone guessing a card without seeing the deck. The issue is that the very structure of quantum results does not match a world where all answers were locally written in advance. Reality is not merely unknown in the ordinary sense. It is not simply keeping secrets from us. Its secrets do not behave like classical secrets. They are woven into relationships that become visible only when separated measurements are compared. And that makes the universe feel less like a warehouse of finished facts, and more like a web of lawful connections, where distance does not allow control, but does allow correlations deeper than classical common sense can comfortably explain. So when you hear that Bell tests rule out simple local hidden variables, do not hear it as dry technical language. Hear it as one of the most profound experimental verdicts in science. The world is not just a set of tiny things carrying private answers through space. Something about reality is more relational, more non-classical, and more subtle than that. The particles do not let us return to the old picture untouched. They do not hand back Einstein's calm universe of local pre-written properties. They give us a stranger universe instead, one where the rules are precise, the predictions are clear, but the meaning keeps opening beneath your feet. The Hong-U Mandel effect shows photon indistinguishability. The deepest clue that two photons are truly identical is not a brighter flash, but the sudden disappearance of a coincidence that should have been there. Imagine two tiny pulses of light approaching the same beam splitter from opposite sides, each one carrying a single photon, each one timed so carefully that they reach the glass at the same instant. To your everyday intuition, this meeting should be easy to picture. One photon might pass through, the other might reflect, and the two might leave by different exits, like two travelers entering a station from opposite doors and walking out separately. But quantum physics quietly removes that ordinary story when the photons are made perfectly indistinguishable. If their color, polarization, timing, and wave packet shape match so well that no possible measurement could tell which photon was which, then the outcome, where they leave separately, disappears. The detectors placed at the two output ports stop clicking together. Instead of one photon at each exit, both photons leave through the same exit, either together on one side or together on the other. This is the Hong-Ou-Mandel effect, first demonstrated in 1987, and it has become one of the clearest tests of photon indistinguishability in quantum optics. What makes it so elegant is that the experiment does not ask you to see the photons directly or paint a visible interference pattern on a screen. It asks you to look for what vanishes, the coincidence count. In a typical setup, one detector waits at each output of the beam splitter. When the photons are not perfectly matched, sometimes the detectors click at the same time, showing that the photons separated. But as scientists adjust the path lengths so the photons arrive together, and as the photons become more alike in every relevant property, those simultaneous clicks fall. On a graph, the result appears as a dip, now famous as the Hom dip, at perfect overlap. In the ideal case, the dip reaches zero, meaning the separated outcome is gone. The photons have become experimentally indistinguishable. This is not because the photons attract each other like magnets, or because one photon pushes the other aside, or because they choose companionship in any human sense. Photons do not have preferences. The effect comes from a more delicate rule. When two alternatives are physically indistinguishable, quantum theory combines them before producing probabilities. For one photon to leave each output, there are two possible stories. Photon A could be transmitted while photon B reflects, or photon A could reflect while photon B is transmitted. If the photons are distinguishable, those stories can remain separate. But if the photons are truly identical, the universe has no physical way to label which story happened. The alternatives overlap, and for the separated output case, they cancel. That cancellation is the heart of the effect. It is not a collision. It is not a force. It is interference between two particle possibilities. This is why the Hong-Ou-Mandel effect is often described as two-photon interference, and why it cannot be understood by treating the photons as simple little marbles moving through glass. The most important word here is indistinguishable, because it does not mean the photons merely look similar to us because our instruments are bad. It means that, in the actual physical conditions of the experiment, the photons share the same relevant quantum mode so completely that no path through the final detection record can tell them apart. If one photon arrives slightly early, the dip becomes shallower. If one has a different color, the dip weakens. If their polarizations do not match, the separated clicks return. The Hom dip therefore becomes a kind of microscope for sameness. It lets researchers test how pure and identical single photon sources are, which is crucial for quantum technologies. In optical quantum computing and quantum communication, photons often need to interfere reliably with photons from other sources. If they carry hidden differences, the interference fails. If they are well matched, the Hom dip reveals it. And this is where the experiment becomes more than a beautiful demonstration. It becomes a tool. The shape and depth of the dip can reveal timing differences, spectral differences, source quality, and coherence. By changing the delay between two photons by incredibly tiny amounts, scientists can watch the coincidence rate rise or fall and infer how well the photons overlap in time. In this sense, the beam splitter becomes a judge of identity. It asks a question no human eye could answer directly. Are these two photons truly the same in the ways that matter? If the answer is no, the photons can leave separately. If the answer is yes, separation cancels itself out. There is a quiet philosophical force in that result, because it challenges the way you think about individuality. In ordinary life, two things can be perfectly similar and still remain two separate individuals. Two identical coins are still this coin and that coin. Two matching keys are still two objects you can track. But photons do not always allow that kind of private identity. If two photons are indistinguishable in the relevant quantum sense, asking which one was transmitted and which one was reflected may not just be difficult, it may be meaningless. The experiment does not hide the labels from you. It removes the labels from the physical description. And when the labels disappear, the possible stories combine and the final outcome changes. That is the lesson the Hom effect gives so gently and so sharply. In the quantum world, sameness is not cosmetic. Sameness has consequences. It changes what can happen. It rewrites the pattern of possible detections. It can erase an outcome that ordinary reasoning expects. So when you imagine the Hong-O-Mandel effect, do not picture two glowing beads bumping into each other at a mirror. Picture two single photons arriving with such perfect overlap that reality itself cannot separate their identities. And because it cannot tell them apart, it refuses to produce the record where they leave alone. The silence between the two detectors is the message. The missing coincidence is the proof. And in that missing click, light teaches one of quantum physics' most unsettling truths. Sometimes two things are not merely alike. Sometimes, for the purposes of nature's deepest rules, they become indistinguishable enough that the universe stops keeping track of which was which. Interaction-free measurement challenges. Direct observation. The strangest kind of seeing is the kind that leaves the thing unseen almost untouched. Imagine a world where every act of looking costs something. To see a snowflake clearly, you must melt it. To test a glass bridge, you must crack it. To prove a whisper exists, you must shout over it. In ordinary life, observation feels harmless, as if the eye simply receives what is already there. But physics has always known that seeing is never perfectly innocent. To see an object, light must bounce from it. To measure a tiny system, some physical exchange must happen. Even the gentlest question has a hand inside it, and when the object is extremely fragile, that hand can destroy what it hopes to know. This is why interaction-free measurement feels so quietly impossible at first. It challenges the old belief that direct contact is the only path to knowledge. It suggests that under carefully designed quantum conditions, you can learn that something is present without the probing particle actually hitting it, without being absorbed by it, without triggering the destructive event that ordinary observation would cause. The idea became famous through the Elitzer-Weidmann bomb tester, where a working bomb is so sensitive that one photon touching its trigger would make it explode. The impossible task is to identify a live bomb without detonating it. Classical logic says you cannot. Either you test it and risk destruction, or you leave it alone and remain ignorant. But quantum mechanics allows a third option. Not always, not perfectly in the simplest version, but genuinely. Sometimes the structure of possible paths changes because the bomb is there, and from that change, you can infer its presence, even though the photon that gives you the information never actually strikes it. This is the heart of interaction-free measurement, and it is not magic, not mind power, not science fiction dressed in lab language. It depends on interference, on the careful splitting and recombining of possible routes, on the fact that a quantum object's behavior is shaped not only by the path it is finally found to take, but by the paths that were available to it. If one possible route contains an absorbing object, the entire interference arrangement changes. A detector that would normally stay quiet may click. That click tells you the object was blocking one path, even though the photon survived and was not absorbed there. The object has been detected by the disturbance it creates in possibility itself. But to say this honestly, we must also say what it does not mean. It does not mean nothing interacted with anything in the broadest possible sense. The object's presence changed the conditions of the experiment. It became part of what the photon's quantum description had to account for. Interaction-free means there was no direct absorbing hit in the successful case, not that the object had no physical role at all. That distinction is important because it keeps the wonder clean. The power of the idea is not that knowledge comes from nowhere. It is that knowledge can come without the usual destructive contact. And this challenges direct observation at its root. For centuries, observation was imagined as a kind of unveiling, as if the world wore a curtain and science simply pulled it back. Interaction-free measurement says sometimes pulling back the curtain burns the stage, and the wiser method is to study how the curtain changes the room without tearing it down. It is a new kind of looking, more patient, more indirect, more respectful of fragility. In later developments, physicists found ways to improve the chances of success using repeated gentle interrogation connected to the quantum Zeno effect, where frequent careful checks can inhibit a quantum change. In simple terms, instead of asking one harsh question, you ask many tiny questions, each so weak that the fragile object is less likely to be destroyed, yet the accumulated answer can still reveal its presence. This is one reason interaction-free measurement is more than a philosophical puzzle. It suggests real methods for imaging delicate systems, especially things that might be damaged by the very particles used to observe them. In principle, if an object is extremely sensitive to light, electrons, or other probes, an interaction-free or reduced interaction approach could help gather information with less damage than direct illumination. This does not make measurement free of limits. Real devices have losses, imperfect detectors, noise, alignment problems, and probabilities that must be respected. But the conceptual shift remains enormous. Measurement does not always need to be a collision. Sometimes it can be an inference drawn from a missing collision, a preserved particle, a changed interference pattern, a path that could have ended in destruction but did not. And when you sit with that, the meaning of seeing begins to widen. Direct observation is powerful because it feels certain. You shine light, the light returns, the image forms, and you trust the result. But quantum physics asks whether certainty always deserves the damage it causes. What if the most intelligent way to know something is not to force it to reveal itself directly, but to arrange the world around it so that its presence becomes unavoidable through what changes nearby? What if the most delicate truths cannot survive the ordinary violence of attention? This is not only a lesson for laboratories, though it must remain grounded there. It is also a way of thinking about knowledge itself. Some things cannot be understood by grabbing them. Some truths disappear when approached too aggressively. Some systems reveal themselves only through their influence on surrounding possibilities. Interaction-free measurement does not say the universe is easy to know. It says the opposite. The universe is so subtle that even knowing must become subtle. The experiment teaches humility. It tells you that the absence of damage can be part of the evidence, that the lack of explosion can speak, that survival itself can be a signal. And perhaps that is why the idea feels so haunting. A direct measurement says, I know because I touched. An interaction-free measurement says, I know because the world changed around what I did not touch. The first feels like certainty through force. The second feels like certainty through restraint. At the quantum level, restraint can become an instrument. Silence can become a detector. A path not taken can still shape the result. So when you hear that interaction-free measurement challenges direct observation, do not imagine a loophole that lets us spy on reality without consequence. Imagine something more profound and more careful. A universe where the possibility of contact can leave a measurable shadow, where fragile things may sometimes be detected without being destroyed, and where the deepest act of seeing is not always to stare harder, but to ask a question so delicately that reality answers without shattering in your hands. The Mach Zehnder interferometer makes paths uncertain. A path can become uncertain, not because the particle is lost, but because the experiment is built so well that the idea of a single road stops making sense. Imagine a tiny pulse of light entering a square-shaped arrangement of glass and mirrors, clean enough to feel almost like a thought made visible. First a beam splitter, then two separate arms, then mirrors guiding the two possibilities around the corners, then a second beam splitter, where the routes meet again, before the final detectors wait for an answer. This device is called the Mach Zehnder interferometer, and at first it looks almost too simple to unsettle reality. It seems like a clever optical maze. Light enters, light is divided, light travels, light returns, light is detected. But the deeper you look, the more the word path begins to weaken. In the everyday world, a path is a fact. You walked through the left door or the right door. A train took one track or another. A drop of rain slid down this side of the window, not that side. But in a Mach Zehnder interferometer, when the system is aligned so that the two arms can recombine without leaving any clear record of which route was taken, a single photon does not behave as though it simply chose one arm in the ordinary classical sense. It is detected as one whole event at the end, yes, but the probabilities of where it appears depend on both arms being available and on the relative timing between them. If one arm is made slightly longer, or if a thin piece of glass is placed in one path, changing the phase of that route, the final detector clicks shift in a predictable way. One detector may become more likely, then less likely, then bright again as the phase is adjusted. This is the interferometer's quiet message. The photon's final behavior is shaped by the relationship between the two possible paths, even when only one detection event occurs. The uncertainty is not ordinary ignorance, like forgetting which hallway someone used. It is not merely that the photons secretly took one route and we failed to check. The whole point of the interferometer is that under the right conditions, the alternatives remain coherent enough to act together. They are not separate classical stories waiting in the dark. They are possibilities that can still be compared, combined, and made to influence the final result. This is why the Mach Zehnder interferometer is so powerful as a teaching tool. It separates two ideas people often confuse. One idea is not knowing. The other is quantum uncertainty. Not knowing is what happens when a coin is under a cup and you have not lifted the cup yet. Quantum uncertainty is stranger. It can mean that the experiment does not support the statement, the photon definitely took this path, unless you add a device that makes the path distinguishable. If both paths are open, stable, and recombined, the final pattern tells you that the photon's quantum description involved the full arrangement. But if you place a path marker in one arm, something that leaves even a subtle trace of which route the photon used, the interference weakens or disappears. The experiment has changed from one that asks about phase and recombination to one that asks about route. And nature does not give both answers with full clarity at the same time. This is not a failure of technology. It is a principle. The more path knowledge you make available, the less interference visibility remains. The more interference you preserve, the less definite the path can be said to be. The Mach Zehnder interferometer makes that trade-off almost visible. It lets you tune reality's answer by changing the way the question is physically arranged. Leave the paths indistinguishable, and the detectors respond to the combined possibilities. Mark the paths, and the combined effect fades. The uncertainty then is not chaos. It is controlled, structured, and experimentally precise. You can adjust a mirror by a tiny amount and watch the probabilities move. You can insert glass and shift the outcome. You can remove the recombining element and make the apparatus behave more like a path detector. This is why the device appears again and again in quantum optics, quantum information, and foundational experiments. It is a clean stage where the old question, which way did it go, can be exposed as too simple. In ordinary language, we want to imagine the photon as a traveler moving through one arm while the other arm stays empty, like a person choosing one corridor in a museum. But the interferometer says that if no route information exists and the paths are recombined, the empty corridor picture does not explain the observed results. The unused path, if you insist on calling it unused, still seems to matter in the mathematics of the outcome. A change in either arm can change the final detections. This does not mean a little ball split in half. It does not mean a ghost photon floated through the other arm in a magical way. It means the quantum state was arranged across alternatives, and the final measurement could not be described by pretending only one route mattered all along. That is the discipline of the experiment. It refuses both childish pictures, the photon as a simple marble, and the photon as a soft classical wave smeared in an ordinary way. It gives you a single click at the end, but the click belongs to a history whose path cannot be drawn like a line on a map. And that is where the topic becomes quietly philosophical. Human beings love paths because paths make stories easy. You were born here, you went there, you chose this, you became that. A path gives comfort because it turns life into a line. But the Mach-Zehnder interferometer asks you to imagine a layer of nature where outcomes depend not on one visible road, but on the preserved relationship between alternatives. It is not telling you that your life is literally a photon in a lab. It is simply reminding you that reality, at its most delicate scale, does not always honor the storytelling habits of the human mind. Sometimes what matters is not which path was taken, but whether the paths remained able to speak to each other. Sometimes a result is born from comparison, not travel. Sometimes certainty is not waiting behind a curtain. It is created only when the experiment allows one kind of question and excludes another. So when you picture the Mach-Zehnder interferometer, do not see only mirrors and glass. See a quiet machine for testing the meaning of where. See two paths that can be physically separated and yet remain part of one quantum question. See a final click that looks simple only after the apparatus has done something profound. It has allowed possibility to meet itself again. And when the detector finally responds, the lesson is not that the photon was confused. The lesson is that your classical idea of a path was too narrow for the kind of truth the interferometer was built to reveal. Weak measurement. Peaks without fully disturbing. The gentlest measurement in quantum physics is not a spotlight, but a barely opened curtain. Imagine trying to learn whether a sleeping bird is in a room without waking it, not by throwing the door open, not by turning on bright lights, not by clapping your hands and forcing an answer, but by letting the floorboards creak so softly that only after listening many times do you begin to sense where the weight might have been. That is the strange spirit of weak measurement. An attempt to peek at a quantum system without forcing it to give up everything at once. In ordinary measurement, the question is sharp and demanding. You ask, "Where are you?" or "Which state are you in?" And the system answers in a way that usually destroys the delicate spread of possibilities it had before. It is like touching a soap bubble to know its shape. The contact gives information, but the bubble may not survive the contact. Weak measurement tries something subtler. Instead of asking one strong question that grabs the system and pins it down, it lets the measuring device interact only very slightly. So slightly that the individual result is almost useless by itself. One weak reading may be noisy, uncertain, barely more than a whisper buried in static. But if the same preparation is repeated many times, and the tiny nudges are collected with care, a pattern can emerge. The system has been disturbed, yes, because no real measurement is completely free, but it has not been fully collapsed in the harsh way a strong measurement would cause. This is why the word weak matters. It does not mean careless. It does not mean vague in the sloppy sense. It means deliberately gentle, deliberately limited, a way of taking only a little information from each quantum system so that some of its fragile behavior can still continue. The idea is especially powerful because quantum systems are not like sealed boxes containing simple hidden labels. If you measure too strongly, you may learn one fact while destroying the very interference or coherence you wanted to study. Weak measurement offers a compromise. It says, ask softly, accept uncertainty, repeat patiently, and you may learn something about the system's hidden tendencies without fully forcing it into a single classical answer. A useful way to picture it is to imagine a compass needle so light that a strong gust would slam it against one side and ruin the reading. A weak measurement is like breathing near it rather than blowing. The needle moves a little, not enough to give full certainty in one attempt, but enough that repeated gentle shifts reveal a direction. In quantum laboratories, this can be done by coupling the system very faintly to a measuring pointer, a beam of light, or another physical device. The pointer barely moves. Most of the time, any single pointer shift is too small to trust. But across many trials, the average shift carries information. This has allowed physicists to explore questions that would otherwise be hidden by stronger measurement, including how quantum states evolve between preparation and final detection, how tiny optical effects can be amplified, and how certain features of quantum systems can be inferred without completely destroying the behavior under study. One of the most famous and mind-bending parts of weak measurement is something called a weak value. In some experiments, you first prepare a quantum system in a particular way, then later keep only the cases where it is finally detected in a chosen outcome. Between those two moments, a weak measurement can reveal a value that may look surprising, sometimes even lying outside the range you would expect from an ordinary strong measurement. This does not mean nature is broken or that instruments are seeing impossible magic. It means the weak value is not the same kind of thing as a normal measurement result from one particle. It is a statistical feature of a carefully selected ensemble, shaped by both how the system was prepared and how it was later filtered. That distinction keeps the science honest. Weak measurement does not let you spy on a single quantum object with perfect clarity while leaving it untouched. It does not bypass the rules. It does not give forbidden knowledge for free. What it gives is more delicate. A way to gather partial information while preserving enough of the system's quantum character to ask questions that strong measurement would erase. This is why weak measurement feels so different from the dramatic experiments where a detector clicks and a result becomes final. Here, the story is not one loud answer. It is many faint answers gathered like dew. The truth appears not as a hammer strike, but as an average, a drift, a slight tilt repeated until it becomes meaningful. And that is a beautiful lesson about quantum knowledge. Sometimes trying to know too much too quickly destroys the very thing you are trying to understand. Sometimes the correct method is not force but restraint. The weak measurement does not storm into the quantum world demanding a confession. It listens at the threshold. It accepts that one whisper is not enough. It builds knowledge slowly, through patience and repetition. This has also made weak measurement useful in precision science, because weak values can sometimes amplify tiny effects. Researchers have explored them for detecting extremely small shifts in light beams, small rotations, or subtle changes that might otherwise be difficult to notice. There is debate about when this gives a practical advantage, and when ordinary methods can do just as well, but the conceptual value remains profound. The act of measuring can be tuned. Measurement is not just an on or off switch between ignorance and certainty. It has strength. It has texture. It can be harsh or gentle, invasive or delicate, final or partial. That idea changes the way you think about observation itself. In the classical world, a measurement seems like a photograph. You point the camera, capture the scene, and move on. In the quantum world, measurement is more like entering a room where the air is so sensitive that your presence changes the dust patterns. A strong measurement opens the window and lets the wind rush in. A weak measurement steps softly, changes the room only a little, and later studies the faint traces left behind. It is not perfectly invisible, but it is careful. And perhaps that is the quiet philosophy hidden inside the physics. Not every truth should be seized. Not every delicate thing can survive a direct question. Some realities must be approached with softer instruments, slower attention, and a willingness to accept uncertainty as part of the price of learning. Weak measurement teaches that knowledge can be partial and still valuable, uncertain and still real, gentle and still scientific. It reminds you that the universe does not always reward the strongest gaze. Sometimes it rewards the most patient one. So when you hear that weak measurement peaks without fully disturbing, do not imagine a magical eye looking without consequence. Imagine a tiny touch so light that the quantum system is not forced completely into one answer. A faint pointer shift repeated across many trials. A careful method that learns from averages rather than domination. And in that quiet space between not knowing and forcing certainty, quantum physics reveals one of its most human lessons. Sometimes the deepest understanding begins when you stop trying to grab reality and learn how to listen to it softly enough that it can keep breathing. Single-electron interference proves matter waves. An electron is not supposed to behave like a ripple, and yet, when you send it through the right experiment alone, patiently, one at a time, it writes waves into the world. Imagine something you were taught to picture as a tiny speck of matter, a charged little point, a building block with mass, something far closer in your mind to dust than to light. Now place that electron in a laboratory where it is released gently toward a barrier, a crystal, or a carefully shaped electric field, and watch what happens not as a crowd, not as a beam so thick that the particles might be pushing one another, but as single arrivals. One electron lands, then another, then another. Each one appears on the detector as a small localized mark, a definite event, almost like a grain of sand hitting a surface. At first, nothing seems strange. The marks look scattered, individual, ordinary. But as more electrons arrive under the same conditions, a hidden pattern begins to gather. Bright and dark regions form. Bands appear where many electrons land, and quiet regions appear where few or none do. The final image is not what you would expect from tiny pellets thrown through space. It is an interference pattern, the signature of wave behavior. And this is why single-electron interference is so powerful. It shows that wave-like behavior is not just something light does, and not just something produced by many particles acting together. Matter itself, even an electron sent alone, follows rules that require a wave description. This idea began as one of the most daring proposals in 20th century physics. Louis de Broglie suggested that if light, which had long been understood as a wave, could also behave like particles called photons, then perhaps matter, which seemed particle-like, could also have wave-like properties. It was a bold symmetry, almost too elegant to trust at first. Maybe every moving piece of matter carries a wavelength, not because it is literally sloshing like water, but because its quantum state spreads and evolves in a wave-like way. The faster the particle moves and the more momentum it carries, the shorter this associated wavelength becomes. For large objects, like a stone, a person, or even a dust grain, the wavelength is so unimaginably tiny that wave behavior is completely hidden in daily life. But for electrons, which are light enough and small enough, the wavelength becomes large enough to measure. That is where the idea stopped being philosophy and became experiment. In the 1920s, electron diffraction experiments showed that electrons scattered from crystals in patterns similar to waves reflecting from regularly spaced atomic layers. The Davison-Germer experiment, for example, sent electrons toward a nickel crystal and found scattering peaks that matched the predictions of de Broglie's matter waves. This was not just a curious result. It was evidence that electrons, the very particles that help make up atoms and electrical currents, could behave as waves when interacting with the ordered structure of matter. Later experiments made the lesson even more direct and visually haunting by sending electrons one at a time and watching the interference pattern build slowly from individual detections. That slow construction matters because it removes a simple escape route. You cannot say the pattern appears because the electrons are bumping into one another or arranging themselves as a crowd. If the beam is weak enough that each electron passes through the apparatus alone, and the pattern still emerges after many repetitions, then the wave-like behavior belongs to each electron's quantum description. Each electron does not draw the whole pattern in one event. It leaves one dot, but the chance of where that dot appears is governed by a wave-like rule, and over time, the rule becomes visible. This is the deep strangeness of matter waves. The electron is detected as a particle, but its motion cannot be fully explained as a particle following one ordinary path like a tiny bead. The wave is not a physical ocean wave made of electron substance spreading through space in the familiar sense. It is a wave of probability amplitude, a mathematical and physical description that tells us where outcomes are more or less likely to appear. That may sound abstract, but the marks on the detector are not abstract. They are real. The interference bands are real. The electron's wave nature is not an optional interpretation added afterward. It is required to predict the observed pattern, and this is why the phrase matter waves is so important. It does not mean matter is secretly soft or unreal. Your hand does not pass through a table because both are waves. The table remains solid to you because enormous numbers of particles interact, bind, repel, and organize into stable structures, while their individual quantum wave behavior becomes hidden inside the larger classical world. But at the scale of a single electron, before the world has averaged away the strangeness, matter reveals its deeper grammar. It does not simply travel like a miniature planet. It spreads in possibility, responds to phase, bends around obstacles, diffracts through openings, and forms interference under the right conditions. Even electron microscopes depend on this truth. They can image extremely small structures because electrons have wavelengths much shorter than visible light, allowing finer detail than ordinary optical microscopes can reach. So the same idea that feels almost dreamlike in a foundational experiment becomes a practical technology used to see viruses, materials, crystals, and nanoscale structures. That is one of the beautiful tensions of quantum physics. Its strangest principles are not just philosophical puzzles. They become tools. Matter waves are not a decorative metaphor. They are why electron diffraction can reveal crystal structure. They are why electron microscopes can open hidden worlds. They are why the old division between particle and wave had to be rewritten, not as a simple either-or choice, but as a deeper framework where quantum objects show different aspects depending on how they are prepared and measured. Still, the single-electron interference experiment keeps its quiet emotional force because it shows this truth in the simplest possible rhythm. One mark, one mark, one mark, then suddenly a pattern too broad for any one mark to explain. It teaches you that reality can be lawful without being predictable in the ordinary sense. You may not know where the next electron will land, but you can know the shape that many landings will form. You may not be able to picture the electron as a tiny ball with a clear route, but you can predict the interference pattern with extraordinary accuracy. The universe is not being vague because it is confused. It is precise in a language older and stranger than human intuition. And perhaps that is why this experiment stays with you. It shows matter becoming mysterious without becoming false. It shows the solid world resting on rules that do not feel solid at all. It shows that even the electron, one of the basic ingredients of ordinary matter, carries a wave-like nature that only appears when you give it the right stage and enough patience. So when you hear that single electron interference proves matter waves, do not imagine a tiny object pretending to be a water ripple. Imagine something more subtle and more real, a single quantum particle arriving as a point again and again, while its hidden wave-like law slowly writes an interference pattern across the detector. The electron is not less real because it behaves this way. It is more astonishingly real than the old picture allowed. It is matter with a rhythm inside it, substance guided by possibility. A small charged thing that teaches you the physical world is not built from hard little pieces alone, but from patterns that only reveal themselves when you stop demanding that nature look like the world your eyes evolved to see. Loophole-free experiments tighten the evidence. The most powerful experiments in quantum physics are not always the ones that reveal something new, but the ones that remove the last comfortable places where doubt could hide. Imagine a courtroom where reality itself is on trial, and for decades the evidence has looked overwhelming. But every time the verdict seems close, someone points to a small unlocked door at the back of the room. Maybe the detectors missed too many particles. Maybe the two measuring stations secretly influenced each other. Maybe the choices of what to measure were not really independent. Maybe the strange quantum result is only strange because the experiment left a narrow escape route open. These escape routes are called loopholes, and in Bell tests they matter deeply because Bell experiments are not just asking whether quantum theory gives the right numbers. They are asking whether the world can still be explained by a simple local realist picture. The old comforting idea that particles carry definite hidden answers with them, and that nothing happening here can instantly affect what is real far away. Early Bell tests gave strong support to quantum mechanics, but they often left one major worry unresolved. Some closed the locality loophole by separating measurement stations so far apart and choosing settings so quickly that no ordinary light-speed signal could pass between them in time to coordinate the results. Others closed the detection loophole by using detectors efficient enough that researchers did not have to assume the detected particles were a fair sample of all the particles produced. But closing both at once was extremely hard. If you separate particles far apart, you often lose more of them. If you detect them efficiently, they may be harder to separate and measure quickly. The experiment becomes a delicate balancing act between distance, speed, randomness, efficiency, and statistical strength. That is why loophole-free Bell tests were such a major turning point. The phrase does not mean every philosophical escape route in the universe has been destroyed forever. It means the most important experimental loopholes, especially locality and detection, were closed together tightly enough that the old simple local hidden instruction story became dramatically harder to defend. In 2015, 3 landmark experiments changed the landscape. One used electron spins in diamond, separated by about 1.3 kilometers, and reported a Bell inequality violation designed to avoid the need for extra assumptions that had affected earlier tests. 2 others used entangled photons with high efficiency detection and fast random measurement choices, reporting significant loophole-free Bell violations with optical systems. The details are technical, but the central idea is beautifully simple. First, you create pairs of entangled particles. Then you send them toward 2 distant stations. At each station, a measuring device randomly chooses which question to ask the particle, and the result is recorded. After many trials, the results are compared. If the particles were merely carrying local pre-written answers, the correlations should obey Bell's limit. If quantum mechanics is right, the correlations can cross that limit. The experiments found the quantum kind of correlations. But what made these newer tests so important was not only the violation itself. It was the care taken to make sure the violation could not easily be dismissed as an artifact of missed particles or hidden communication between stations. The detection loophole is like a biased survey problem. If your detectors miss too many particles, a skeptic can say, maybe you only detected the pairs that happened to fit the quantum prediction, while the missing pairs would have restored the classical pattern. Closing that loophole means detecting enough events and designing the analysis carefully enough that this kind of sampling excuse no longer works. The locality loophole is different. It worries that one side of the experiment might somehow learn what setting or result occurred on the other side before producing its own result. To close it, the measurement choices and outcomes must be arranged so that any ordinary signal traveling at or below the speed of light would arrive too late to explain the correlation. That is why distance, fast switching, and timing are not minor engineering details. They are part of the philosophical backbone of the experiment. The freedom of choice concern adds another layer. If the measurement settings are predictable or secretly correlated with the source, then a hidden variable model might use that pattern. So experiments use random number generators and careful timing to make the measurement choices as independent as possible. None of this makes the laboratory feel like a magical place. In fact, it makes it feel more impressive because it is so disciplined. The strangeness is not protected by vagueness. It is protected by precision. Every cable length, every detector efficiency, every timing window, every statistical test becomes part of the argument. The experimenters are not merely trying to see a weird quantum effect. They are trying to deny nature every ordinary excuse. And after those excuses are removed, the result remains. Entangled particles produce correlations stronger than any simple local realist theory should allow. This does not mean entanglement lets us send messages faster than light. It does not. The individual outcomes still look random, and only later comparison reveals the correlation. It also does not mean science has ended the debate about every possible interpretation of quantum mechanics. Some interpretations accept non-locality in a hidden way. Some philosophical positions try to question the independence of measurement choices. But the experiments have tightened the evidence until the old easy answer, the particles just carried local secret instructions all along, no longer survives as a simple explanation. That is the quiet power of loophole-free tests. They do not add a new fantasy to quantum physics. They remove the fantasy that the strangeness was probably just a flaw in the equipment. They force the mystery to stand in cleaner light. And maybe that is why this topic feels different from the more visually dramatic quantum experiments. There is no single image here as poetic as dots forming bands or light vanishing from one output. Instead, the drama is in the closing of doors. One loophole shut, then another, a detector made more efficient, a station moved farther away, a setting chosen faster, a timing condition tightened, a statistical doubt reduced. the experiment becomes a kind of careful silence around the result, stripping away every ordinary noise until the quantum correlation is still there, steady and unembarrassed. In the end, loophole-free Bell tests do not make reality less mysterious. They make the mystery harder to escape. They tell you that the universe is not merely hiding classical answers behind bad instruments. Something deeper is happening in the way distant quantum systems are related, something that respects the rule against faster-than-light messaging, yet refuses to fit into the old picture of separate objects carrying complete local facts. And as the evidence tightens, the question becomes softer but heavier. If the world is not built from the kind of separateness our intuition expects, then how much of what we call ordinary reality is only ordinary because we have never looked carefully enough to close the loopholes? Entangled photons can be sent through fiber. A thread of glass thinner than a strand of hair can carry two particles that still behave as though distance has not fully separated them. Imagine an ordinary fiber optic cable buried beneath a city, the same kind of hidden line that helps carry phone calls, video streams, bank transfers, and the quiet machinery of the modern internet. And then imagine that inside this glass path, alongside all the ordinary pulses of information, scientists send something far more delicate, photons whose properties are entangled before they ever enter the cable. These photons are not carrying a secret message in the usual sense, and they are not tiny flashing beads with instructions written inside them. They are part of a shared quantum state, prepared together in such a way that measuring one later helps define the correlated result of the other, even after they have traveled through different routes. The astonishing part is not simply that photons can move through fiber. Light does that every day. The astonishing part is that entanglement, one of the most fragile and non-classical features in physics, can survive the journey through real optical fiber long enough to be measured at distant stations. This turns fiber from a simple communication tube into something closer to a quiet quantum bridge. In the laboratory, entangled photon pairs are often created using a process where a stronger laser beam passes through a special crystal or optical material and rarely produces two lower energy photons whose properties are linked. Those properties might involve polarization, meaning the orientation of the light's electric field, or time-bin states, meaning the photon is in a carefully prepared early or late timing structure. Time-bin entanglement is especially useful in fiber because polarization can twist and drift as light moves through glass, while timing differences can remain more stable over long distances. Once created, the photons can be sent into optical fibers towards separate detectors. One photon may travel through one spool of fiber, the other through another, or one may remain nearby, while the other is sent farther away. At the end, scientists compare the measurement records. They do not see a glowing thread of connection while the photons travel. They see clicks at detectors, timing patterns, and correlations stronger or more structured than classical intuition expects. The connection is not visible as a rope between them. It is revealed statistically after many pairs have been sent and measured. That is important because it keeps the idea grounded. Entangled photons sent through fiber do not allow instant messaging. They do not let one person control the result at the other end. Each individual detection still looks partly random. The entanglement appears when the two sides later compare their records through normal communication. So the mystery is real, but it is disciplined. It does not break the speed limit of useful information. It simply shows that the paired photons were described by a shared quantum structure that survived their separate journeys. But sending entangled photons through fiber is not easy, because fiber is not a perfect tunnel. It absorbs light slowly, it scatters some photons away. It changes polarization. It spreads pulses in time. It introduces tiny disturbances from temperature, bending, vibration, and imperfections in the glass. Ordinary internet signals solve this problem by using many photons, amplifiers, repeaters, and error correction. If a classical pulse weakens, you can boost it, copy it, reshape it, and send it onward. But quantum information cannot be copied perfectly in that simple way. A single unknown quantum state cannot be cloned without destroying the rules that make it quantum. This makes long-distance quantum communication much harder than ordinary optical communication. Every lost photon is not just a weak signal. It may be a lost quantum event. Every disturbance can blur the delicate correlations. Every detector must be sensitive enough to catch individual photons while ignoring false signals from noise. This is why experiments with entangled photons in fiber are not merely demonstrations of strange physics. They are engineering lessons in how fragile reality can be when you try to use it. Scientists must choose wavelengths that travel well through telecom fiber, often near the same infrared bands used in existing communication networks. They must stabilize paths, control timing, reduce noise, and build detectors that can recognize the faint arrival of one photon among all the possible background. And yet, despite these difficulties, entangled photons have been sent through many kilometers of fiber in research networks, showing that quantum correlations can be distributed through infrastructure that resembles the nervous system of modern communication. This is one reason the topic matters so much. If entanglement can be reliably distributed through fiber, it becomes a foundation for quantum networks, quantum key distribution, secure communication methods based on physics, and eventually links between quantum computers or quantum sensors. In a future quantum internet, information may not travel only as ordinary bits, the simple zeros and ones of classical machines. Some tasks may use entanglement as a resource, allowing distant quantum devices to coordinate in ways ordinary networks cannot. The dream is not a magical internet where thoughts teleport across the planet. The dream is a carefully engineered network where fragile quantum states can be shared, protected, measured, and used for tasks that classical systems cannot easily perform. Fiber is one of the most practical roads toward that dream because it already exists under cities and oceans, already connects laboratories and data centers, already carries light with remarkable efficiency. But the quantum version asks more from the cable. It asks the glass not merely to transmit brightness, but to preserve relationship. And that word, relationship, is the quiet center of the whole idea. An entangled photon traveling through fiber is not valuable only because it is a photon. It is valuable because of what remains linked to another photon, because of a correlation that must survive loss, distance, and noise. The cable does not carry a visible bond. It carries one half of a delicate shared condition. The other half may be elsewhere, waiting behind another detector, in another building, across a city, perhaps eventually across regions connected by repeaters and satellites. And when both sides finally compare what they found, the hidden order appears. There is something deeply poetic, but still scientifically honest, in picturing this. Beneath the ground, inside cold strands of glass, single photons travel silently through the same kind of cables that carry ordinary human conversation. But these photons carry a quieter kind of connection, one that cannot be read by simply looking at one side alone. You need both ends. You need patience. You need comparison. You need the pattern that appears only when separated events are brought back into one story. That is what entangled photons in fiber teach so beautifully. Distance can damage quantum connection, but it does not automatically erase it. Glass can guide not only light, but the possibility of shared quantum structure. And as the photon moves through the cable, it reminds you that the future of communication may not only be faster, louder, or brighter. It may also become more delicate, built from single particles, preserved correlations, careful timing, and the strange fact that even across a dark thread of fiber, nature can carry not just signals but relationships. Satellite experiments test quantum links across Earth. A quantum link across Earth does not look like a glowing bridge in the sky. It looks like a satellite passing quietly through darkness while single photons try to survive the journey between space and the ground. Imagine standing at a remote observatory at night where the air is cold. The telescope is tracking a moving point overhead, and somewhere above the atmosphere a spacecraft is carrying instruments designed not merely to send ordinary signals, but to test whether the fragile rules of quantum physics can stretch over continental distances. Down here, on Earth, light is easily weakened by fiber, scattered by air, swallowed by weather, blurred by turbulence, and drowned by background noise. A photon is so small a messenger that losing it is almost effortless. Yet satellite quantum experiments ask a bold question. Can entanglement, quantum key distribution, and even teleportation-like state transfer work when the two ends of the experiment are separated not by a lab bench, not by a city, but by hundreds or thousands of kilometers across Earth? The answer, carefully built over years of engineering and measurement, is yes. But not in the magical way science fiction would imagine. The satellite does not beam people. It does not send thoughts. It does not allow faster-than-light messages. What it does is use light, timing, telescopes, and quantum states to test whether quantum correlations and secure keys can be distributed over distances too large for ordinary fiber to handle efficiently. The most famous example is China's Mach satellite, part of the Quantum Experiments at Space-Scale mission, launched in August 2016. Within its first year, teams reported satellite-to-ground quantum key distribution over about 1,200 kilometers, entanglement distribution between two ground locations separated by about 1,200 kilometers, a Bell test, and ground-to-satellite quantum teleportation experiments. The reason space helps is surprisingly simple. Photons traveling through empty space lose far less energy than photons traveling the same long distance through optical fiber, because most of the path between a low Earth orbit satellite and a ground station is through near vacuum rather than glass. Fiber is wonderful for cities and regional links, but over very long distances it absorbs light, and quantum states cannot simply be copied and amplified like ordinary internet signals. A satellite can rise above much of that loss, sending or receiving photons through a thinner atmospheric slice, then using ground stations as endpoints. But this creates another difficulty. The satellite is moving fast, the Earth is rotating, the atmosphere is shifting, and the telescopes must point with extraordinary accuracy. A tiny angular error can send the photons into empty sky. A little turbulence can distort the beam. A cloud can stop the experiment completely. Daylight can add too much background noise, which is why many of these experiments prefer darkness. So when people hear quantum satellite, they may imagine a futuristic machine calmly connecting the planet, but the real achievement is more fragile and more impressive. It is a moving spacecraft and distant telescopes catching individual quantum signals through a noisy world. In one major milestone, Misius acted as a trusted relay between China and Austria, helping create secret keys between locations separated by up to 7,600 kilometers. Those keys were then used for real-world demonstrations, including image transmission and a 75-minute quantum-secured video conference between Beijing and Vienna. The words trusted relay matter. In that version, the satellite helps establish separate keys with two ground stations and then assists in combining them so the distant stations can communicate securely. This is powerful, but it means the satellite itself must be trusted. A deeper goal for future networks is to distribute entanglement directly between distant users, or use quantum repeaters and more advanced protocols, so security depends less on trusting intermediate nodes. That is why satellite experiments are not just about sending encrypted messages. They are stepping stones toward a global quantum network, one where space links, fiber networks, and ground stations may work together. The science behind the security is also easy to misunderstand. Quantum key distribution does not make a message magically unbreakable in every practical sense. Real devices can have flaws, and the classical systems around them still need careful security. But the quantum part offers something unusual. If an eavesdropper tries to measure the quantum signals in the wrong way, the act of measurement can introduce detectable disturbance. In principle, the key can be checked for signs of tampering before it is used. That is why quantum communication is less about hiding a message inside an impossible code, and more about creating a key whose secrecy is protected by physical law, Provided the equipment is built and modeled correctly, satellite tests push this idea into the real world, where photons must pass through atmosphere, optics, motion, timing windows, detector limitations, and environmental noise. Every successful result is therefore not only a triumph of quantum theory, but a triumph of patience. The satellite must know where the ground station is. The ground station must follow the satellite. The photons must be prepared, transmitted, detected, time-stamped, filtered, compared, and statistically analyzed. Most attempts do not produce a useful photon at the end. Loss is normal. Silence is normal. What matters is whether enough events survive to reveal the pattern. And this is where the experiment becomes quietly beautiful. The quantum link is not a cable you can hold. It is a relationship reconstructed from many tiny detections, many missing photons, and many carefully matched time records. A photon leaves a spacecraft or travels upward from Earth, crosses a vast dark distance, enters a telescope, reaches a detector, and becomes one click among many. Alone, that click is small. Together with its partner records, it becomes evidence that quantum states can be shared over planetary scales. It means the same laws tested on tables in laboratories are not confined to tables. They hold across mountains, cities, deserts, continents, and the edge of space. The universe does not stop being quantum when the distance becomes inconvenient. It only becomes harder for us to preserve the evidence. And perhaps that is the deeper feeling these satellite experiments leave behind. They turn the sky from a symbol of remoteness into part of the laboratory. They show that the strange delicacy of quantum mechanics can be lifted out of protected rooms and tested against the scale of Earth itself. A satellite passes overhead, almost invisible to the eye, and for a few brief minutes it can connect stations thousands of kilometers apart with signals so faint that a single photon matters. In that moment, communication becomes less like shouting across distance and more like keeping a fragile promise alive through space. The message is not that distance has been defeated. Distance still causes loss. Atmosphere still interferes. Technology still struggles. The message is subtler. Even across the curve of the planet, with all the noise of the real world in between, quantum relationships can survive long enough to be used, tested, and trusted. And when you imagine those photons crossing the night, you are watching one of the first sketches of a future network, not built only from wires under oceans, but also from silent spacecraft, patient telescopes, and the strange fact that Earth itself can become the stage for quantum connection. Quantum tomography reconstructs the invisible state. A quantum state cannot be photographed, so scientists learned to rebuild its portrait from shadows. Imagine being handed a sealed sculpture made of glass, but every time you shine light from one direction, the sculpture changes slightly, and every photograph shows only a flat shadow, never the whole shape. One shadow tells you something, but not enough. A second shadow helps. A third begins to hint at depth. Only after many views, taken from carefully chosen angles, can you reconstruct what the hidden object must have been like. This is the spirit of quantum tomography, a method for reconstructing the invisible state of a quantum system from many repeated measurements. Not by seeing the state directly, but by collecting enough partial evidence to infer its structure. The word tomography may remind you of a medical CT scan, where many X-ray images taken from different angles are combined to build a picture of the inside of a body. Quantum tomography has a similar emotional shape, but the challenge is deeper. A quantum state is not a little object sitting inside a box with a surface you can photograph. It is the full description of what a system can do when measured in different ways. How likely different outcomes are, how different possibilities are related, whether the system is pure or mixed, whether it contains coherence, whether two parts are entangled, whether the state prepared in the lab is the state the scientist intended. In modern quantum information, this reconstructed description is often represented by something called a density matrix, which is a compact way of storing all the measurable information about the state, including both probabilities and the delicate relationships between possibilities. Quantum state tomography reconstructs that density matrix by preparing the same state many times and measuring those repeated copies in a complete set of measurement settings. This is the first essential truth. Tomography does not reveal the full state of one lonely particle from a single measurement. That would be impossible. A single measurement gives only one outcome, and in quantum physics, the act of measuring usually changes the system. If you measure one copy one way, you cannot then rewind that exact same copy and measure every other aspect of it as though nothing happened. So tomography depends on repetition. The source must prepare many systems in the same unknown state, again and again. Like printing many identical sealed letters. You open different letters in different ways, destroying or changing each one as you read it, but because the preparation is repeated. The collection of partial readings lets you reconstruct the message that none of the individual readings contained alone. Reviews of quantum tomography emphasize exactly this point. An unknown quantum state cannot be inferred from a single system in general. It can be estimated when many identically prepared copies are available, allowing different measurements on different copies. This is why tomography is both powerful and humble. It does not cheat the rules of measurement. It works around them with patience. It accepts that each individual result is limited, then lets statistics gather the hidden shape. For a single qubit, the simplest quantum unit used in quantum computing, you might measure along several different axes, each one giving a different kind of partial answer. One set of measurements tells you one slice of the state. Another set tells you another slice. A third helps complete the picture. No single basis is enough to reconstruct the whole state, because different quantum features cannot all be captured from one measurement perspective alone. Multiple measurement bases and repeated trials are needed to reduce statistical noise and recover a fuller description. And this is where the beauty of the method appears. The quantum state itself remains invisible in the direct sense. You never hold it up to the light and see it glowing. You see detector clicks, counts, frequencies, histograms, little streams of outcomes that look almost dull compared with the grandeur of the claim. Then mathematics gathers those outcomes and asks, what state would most likely have produced this pattern of results? In early, simple versions, scientists used linear reconstruction. In more careful modern work, they often use methods that enforce physically valid states, because raw experimental data can be noisy and imperfect. Real tomography must deal with detector errors, preparation flaws, calibration limits, finite sample sizes, and the fact that every estimate comes with uncertainty. The reconstructed state is not a divine photograph. It is an experimentally supported model, a best reconstruction from the available evidence. And that honesty makes it more impressive, not less. Because science is not strongest when it pretends to see perfectly. It is strongest when it knows exactly how imperfect vision can still be made reliable. Quantum tomography is used to check whether quantum devices are actually preparing the states they claim to prepare. In quantum computing, it helps researchers diagnose whether a qubit rotation worked, whether a gate produced the right state, whether unwanted noise has crept in, or whether an entangled state really has the correlations expected. In photon experiments, tomography can reconstruct the polarization state of light, showing whether the prepared photons are in the desired superposition or entangled condition. In trapped ions, superconducting circuits, and other platforms, tomography becomes a kind of audit trail for the invisible. It asks not merely, did the detector click, but what hidden state best explains the whole family of clicks across many questions. That difference matters because quantum engineering cannot rely on faith. If you want to build quantum computers, quantum networks, or precision sensors, you must verify the fragile states you create. You must know whether your machine is producing the intended quantum resource or only a noisy imitation. Tomography gives scientists a way to turn invisible preparation into visible evidence. But it also has a cost. As quantum systems grow larger, full tomography becomes extremely demanding, because the amount of information needed can grow very quickly with the number of qubits. Reconstructing a small system may be manageable. Reconstructing a large many-qubit state completely can become impractical. This is why researchers also develop alternatives such as partial tomography, compressed sensing, randomized measurements, and classical shadow tomography, which aim to learn useful features without reconstructing every detail of the full state. The goal is not always to know everything. Sometimes the wiser goal is to know the right thing efficiently. That too is a lesson worth hearing. Quantum tomography begins with a dream of complete reconstruction, but modern quantum science often asks a more practical question. Which features of this invisible state matter for the task, and how can we estimate them without drowning in data? Still, the central idea remains deeply moving. A quantum state is invisible not because it is imaginary, but because it is not the kind of thing a single glance can reveal. It is a structure of possible answers, and only by asking many carefully arranged questions can you rebuild its shape. The state is like a song that cannot be heard in one note, a landscape that cannot be understood from one window, a face reflected in broken mirrors that must be patiently aligned. Each measurement gives a fragment. Each fragment is incomplete. But together, if the experiment is designed well, the fragments become a portrait. And the portrait matters because it lets scientists speak with confidence about systems too delicate for ordinary seeing. So when you hear that quantum tomography reconstructs the invisible state, do not imagine a camera taking a forbidden snapshot of a particle's soul. Imagine a disciplined act of rebuilding, many identical preparations, many different measurements, many small outcomes gathered into one inferred description. The invisible is not made visible by force. It is made visible by pattern, by repetition, by asking from enough angles until the hidden structure begins to stand up from its shadows. In that quiet reconstruction, quantum physics teaches one of its most patient truths. Some realities cannot be seen directly, but they can still be known if you are willing to let many partial answers slowly become one shape. Neutron interferometry tests. Quantum phase. A neutron can pass through a crystal as if it is both a traveler and a clock, and the clock can fall out of rhythm even when the traveler still arrives. Imagine holding a particle that has mass like a tiny piece of matter, no electric charge to make it easily pulled around by electric fields, and a quiet internal spin that can respond to magnetism in deeply quantum ways. It is not light, yet it can interfere. It is not a classical bead, yet it can be detected as one event. It can move through carefully grown perfect silicon crystals, be split into separated paths by the crystal's orderly atomic planes, travel along two different arms, and then be brought back together so that its final intensity depends on something almost invisible. Phase. Phase is one of those words that sounds technical until you feel its meaning. Think of two dancers doing the same slow movement. If their steps rise and fall together, they reinforce one another. If one is half a step behind, the meeting changes. Nothing about their bodies has disappeared, but the relationship between their rhythms has shifted. Quantum phase is a little like that, though deeper and stranger. It is not simply where the neutron is, not simply how fast it moves, and not simply how bright the final beam appears. It is the hidden rhythm of the neutron's wave-like description, and neutron interferometry is one of the most beautiful ways scientists have learned to test that rhythm. In a neutron interferometer, the neutron beam can be divided and recombined using a perfect crystal, often silicon, whose lattice acts with a precision that ordinary mirrors could never provide for such particles. Neutron interferometry is used for fundamental tests of quantum mechanics, scattering measurements, and gravity-related experiments. And perfect silicon crystal interferometers have been central to much of this work. What makes neutrons especially powerful is that they are not just another version of photons. They have mass, so gravity can affect the phase between two paths. They have spin, so magnetic fields can rotate part of their quantum state. They can pass through materials and interact with nuclei in ways that reveal scattering lengths and subtle internal structure. A photon interferometer often teaches you how light's possible paths recombine. A neutron interferometer lets you ask a heavier question. Can matter itself carry a phase that responds to gravity, magnetism, rotation, and the hidden geometry of quantum spin? The answer is yes, and one of the landmark examples is the Colella-Overhauser-Werner experiment, often called the cow experiment. where neutrons were coherently split into paths at different heights in Earth's gravitational field and then recombined. The results showed a quantum mechanical phase shift caused by gravity, not as a falling rock would show it, but as a change in the interference of neutron matter waves, moving through different gravitational potentials. This is not the same as simply saying the neutron falls like a tiny ball. The neutron's mass matters, but the measurement is not a photograph of a falling trajectory. It is a phase comparison. One path accumulates a slightly different quantum rhythm from the other because the two paths experience gravity differently, and when they meet again, the shifted rhythm changes the interference pattern. That is the quiet genius of the experiment. Gravity, the most familiar force in your body's daily life, becomes visible not through weight or impact, but through the phase of a single quantum object. It is as if the Earth itself gently retunes one arm of the interferometer, and the neutron returns carrying the difference as a hidden musical delay. This is why phase is so important. A phase shift can be invisible along each path separately, yet become measurable when the paths are reunited. Alone, one path cannot tell you the full story. The meaning appears in comparison. The interferometer becomes a machine for making the invisible relational. It does not ask only, where did the neutron go? It asks, how did one possible history fall out of step with another? And that question opens doors far beyond gravity. With magnetic fields, neutron interferometry can test the quantum nature of spin. A neutron is a spin-half particle, and spin in quantum mechanics does not behave like an ordinary arrow drawn on a ball. One of the most famous lessons is that rotating such a quantum spin through one full turn can change the sign of its wave function, and that only after 2 full turns does it return fully to its original phase relationship. Neutron interferometry helped make this strange spinner behavior experimentally meaningful, showing that what might sound like a mathematical subtlety can become visible through interference. This is deeply unsettling in a gentle way. If you rotate an ordinary object once, it looks the same again. Turn a cup around, and after one full rotation, the handle returns where it started. But the neutron's quantum spin carries a phase structure that is not exhausted by ordinary visual sameness. The world of quantum phase cares about something subtler than appearance. It cares about how the wave function returns to itself. And because interferometry compares one path or one spin condition against another, it can reveal phase changes that no single isolated measurement would make obvious. That is why neutron interferometry feels like listening to a secret layer of matter. It does not merely count particles. It listens for their relative rhythm. It turns hidden phase into bright and dark output beams. It makes the unseen difference between two quantum histories appear as a real change in detector counts. The practical apparatus may look solid and technical. A crystal, a neutron beam, shielding, alignment, detectors, magnetic coils, rotation stages, careful temperature control. But inside that solid machinery, something almost poetic is happening. Matter is being split into alternatives, not as a broken object, but as a coherent quantum state. Those alternatives are allowed to experience the world differently. One may feel a different gravitational height. One may pass through a magnetic region. One may acquire a different phase from a material. Then they are reunited, and the final interference reveals what the neutron carried back from those different experiences. This is not fantasy. It is why neutron interferometry became such a powerful laboratory for fundamental physics. It tests not only whether quantum particles can interfere, but what invisible influences can write themselves into the phase before interference occurs. And maybe that is the deeper lesson for the listener. We often think reality is made only from visible changes. A door opens, a glass falls, a light flashes, a detector clicks. But neutron interferometry teaches that some of the most important changes happen in the relationship between possibilities. Nothing dramatic has to happen along one path. The neutron does not need to explode, glow, or leave a trail. A tiny phase shift, carried silently through the experiment, can later reshape the whole pattern. The evidence appears only when the two histories meet again. That is why quantum phase is so powerful and so difficult to picture. It is not a property you can hold in your hand. It is a difference that becomes real in reunion. It is a hidden rhythm made measurable by comparison. So when you hear that neutron interferometry tests quantum phase, do not imagine only a particle passing through a machine. Imagine a massive quantum object being divided into possible histories, each history gathering a slightly different rhythm from gravity, spin, or matter, and then returning to meet itself inside a crystal so perfect that the smallest mismatch can be heard as a change in the final signal. The neutron arrives as a particle, but the phase it carries proves that its story was never just a particle's path. It was a quiet conversation between matter and the invisible rhythms of the universe. Molecule interference pushes quantum weirdness bigger. A molecule should be too busy to behave like a ghost, and yet under the right conditions, it can cross an experiment as if its entire many-atom body is guided by a wave. Think about what a molecule really is. Not a clean little dot, not a single photon, not one simple electron, but a crowded structure of atoms tied together, vibrating, rotating, storing heat, carrying chemical bonds, and constantly threatening to reveal too much about itself to the surrounding world. A molecule is messy in a way a single particle is not. It has shape, it has size. It may twist, bend, and flex. It may contain dozens, hundreds, even thousands of atoms. And because of that, it feels as though quantum weirdness should fade before it reaches something so complicated. You can almost hear common sense whispering, maybe the tiny world is strange, yes, but surely a large molecule must behave more like a tiny grain of dust than like a wave of possibility. Surely, once matter becomes complex enough, warm enough, heavy enough, crowded enough inside, the quantum mystery should disappear. But molecule interference experiments were designed to test exactly that feeling, and the answer is not comforting. Large molecules can produce interference patterns too, not because they are weightless, not because they are simple, not because they are imaginary, but because quantum mechanics does not draw the border between weird and ordinary where human intuition wants to draw it. The challenge is not whether the quantum wave nature exists in principle. The challenge is whether it can survive long enough to be seen before the environment destroys its delicate coherence. To understand this, imagine sending a beam of large molecules through a carefully engineered interferometer. You cannot treat them casually. If the molecules collide with air, the pattern can be washed away. If they emit or absorb too much heat radiation, they may leak information about their position. If the apparatus vibrates, if the beam is too broad, if the detection is too rough, the quantum signature fades into ordinary blur. So the experiment must become almost ceremonial in its precision. High vacuum, controlled molecular beams, nanostructured gratings, careful timing, and detectors sensitive enough to count where the molecules finally arrive. In some of the classic experiments, fullerene molecules such as C60 and C70, carbon structures shaped almost like tiny molecular soccer balls, were sent through interferometers and shown to produce wave-like interference, proving that even relatively large, internally complex molecules could display quantum behavior when isolated well enough. A Talbot-Lowe interferometer was especially important because it could handle larger and more complex particles than many simpler far-field arrangements, making the wave nature of fullerenes experimentally visible rather than just mathematically expected. And then the boundary kept moving. Scientists did not stop with small molecules. They pushed toward heavier organic compounds, tailor-made molecular systems, and eventually huge molecules made from thousands of atoms. In one major milestone, experiments reported matter wave interference from functionalized oligoporphyrin molecules with masses beyond 25,000 atomic mass units and up to roughly 2,000 atoms, showing that quantum superposition could be demonstrated in objects far larger and more structurally complicated than the early fullerene tests. That number matters because it forces the imagination to stretch. A molecule with thousands of atoms is not a tiny point in any intuitive sense. It is a whole architecture of nuclei and electrons, internal vibrations and chemical structure, a little moving cathedral of matter. And yet, when prepared and isolated correctly, its center of mass motion can still behave as a matter wave. That phrase, center of mass motion, is important because it keeps the science honest. The entire molecule is not necessarily floating around like a visible cloud in the dreamy way people sometimes imagine. Its internal parts may be vibrating and rotating, but the motion of the molecule as a whole can still show interference. The pattern does not mean the molecule is unreal. It means that the molecule's possible paths through the apparatus retain a quantum relationship long enough to overlap and produce measurable fringes. Each molecule is detected as a localized object, one final arrival, but the distribution of many arrivals reveals the wave-like rule that guided the journey. And this is where the experiment becomes a quiet confrontation with the classical world. If electrons interfere, you can tell yourself electrons are tiny. If photons interfere, you can say light has always been wave-like anyway. But when a large molecule interferes, your excuses begin to run out. The question changes from can quantum objects be strange to how large can the strangeness remain visible before the world notices too much? That noticing is called decoherence. It is not a mysterious collapse caused by human thought. It is the gradual loss of quantum interference when a system becomes entangled with its environment. Air molecules, thermal radiation, vibrations, stray fields, and uncontrolled interactions can all carry away information about where the molecule might have been. Once the environment holds that information, even in principle, the interference becomes harder or impossible to observe. In this sense, the classical world is not necessarily a separate kingdom with different laws. It may be what quantum behavior looks like after countless tiny interactions have blurred the delicate relationships between alternatives. Molecule interference experiments are so powerful because they let scientists study that border directly. They ask, how much mass, how much complexity, how much internal motion can a quantum wave tolerate? How isolated must something be before its hidden wave nature can still speak? And the answer keeps becoming larger than expected. Even biological or bio-related molecules have been tested in matter wave interference contexts. For example, a native polypeptide, a molecule related to the building blocks of proteins, has been shown to display matter wave interference using an optical Talbot-Lowe technique, extending the question of quantum behavior toward more complex chemical and biological structures. This does not mean living animals, people, or ordinary objects are about to visibly interfere like waves in daily life. That would be misleading. A human body is constantly interacting with air, light, heat, the ground, its own internal chemistry, and the surrounding world so intensely that any large-scale quantum coherence of that kind would vanish almost instantly. But the molecule experiments still teach something profound. The reason you do not see chairs and hands making interference patterns is not because quantum theory simply stops applying. It is because maintaining coherence becomes overwhelmingly difficult as systems grow larger, warmer, and more exposed. The weirdness is not necessarily absent. It is hidden, drowned, decohered, averaged out by the noise of the world. And recently, the scale has been pushed even further beyond ordinary molecules. A 2026 Nature report described matter wave interference with sodium nanoparticles containing more than 7,000 atoms and masses greater than 170,000 daltons, extending interference to a new class of massive metal clusters and surpassing previous macroscopicity benchmarks. This is not exactly the same as saying a rock is in two places at once in the way a cartoon would show it. It is a carefully controlled quantum interference experiment with highly prepared particles under extreme conditions. But that is precisely why it matters. The truth does not need exaggeration. The real achievement is already strange enough. Scientists are learning how far quantum wave behavior can be preserved as objects become heavier, hotter, and more complex. Every successful interference experiment with larger matter pushes the boundary between the quantum and classical worlds farther away from our instincts. It tells us that the line may not be a hard wall at all, but a gradual fading caused by interaction, information leakage, and practical difficulty. And perhaps that is the deepest lesson hidden inside molecule interference. The world you see as solid and ordinary may not be built from ordinary ingredients. It may be built from quantum possibilities that only look classical because they are constantly being monitored by the environment, not by conscious eyes but by collisions, radiation, and entanglement with everything around them. A molecule in a vacuum, protected from the noise, can briefly reveal that buried ancestry. It can move through an experiment not like a tiny billiard ball, but like a possibility spread across paths, carrying a wave nature that seems too delicate for something so large, and yet appears in the final pattern. So when you hear that molecule interference pushes quantum weirdness bigger, do not imagine scientists making fantasy objects vanish or split like magic. Imagine something more careful and more astonishing. A complex molecule, heavy with atoms and internal motion, traveling through a near-silent apparatus, avoiding the touch of air and heat just long enough for its hidden wave rhythm to survive. Then imagine many such molecules arriving one by one, each leaving a small mark, until the marks gather into a pattern that says the old boundary was never where you thought it was. Quantum weirdness did not belong only to the tiny. It was waiting inside matter itself, and every larger interference experiment is another quiet reminder that the ordinary world may be quantum reality wearing the mask of noise. Experiments keep making the weirdness harder to deny. The strangest ideas in quantum physics have survived the one thing that should have destroyed them: better experiments. At first, it is easy to imagine quantum weirdness as a fragile mistake from the early days of science, something born from crude instruments, incomplete theories, dim photographic plates, or physicists trying too hard to explain tiny things they could barely control. Maybe the particles only looked strange because the measurements were clumsy. Maybe the patterns were caused by hidden disturbances. Maybe the correlations were statistical accidents. Maybe the old experiments left too much room for doubt. This is the comforting thought people often reach for when quantum physics becomes too unsettling. Perhaps the weirdness is not in nature, but in our ignorance. And for a while, that kind of doubt was reasonable. Science should doubt. Science should be suspicious of its own astonishment. A strange result is not enough. A beautiful theory is not enough. A dramatic laboratory image is not enough. The real test is whether the strangeness remains when the instruments improve, when the experiments become cleaner, when the loopholes close, when independent teams repeat the work, when the same impossible-looking principles begin to appear in completely different systems. And that is exactly what happened. Quantum weirdness did not fade under sharper scrutiny. It became harder to deny. The more carefully scientists looked, the less the universe resembled the old classical picture. Early quantum experiments already hinted that light and matter could not be understood as simple objects following simple paths. But modern experiments have gone much further. They do not merely watch nature behave strangely. They prepare quantum systems, isolate them, manipulate them, measure them from different angles, and test whether the strangeness is real enough to survive engineering. A single atom can be trapped and cooled until its quantum state can be controlled. A single ion can be made to behave like an artificial quantum system inside an electromagnetic cage. A superconducting circuit, large enough to be built by human hands and placed on a chip, can show quantum behavior usually associated with atoms. Photons can be entangled, routed through fibers, sent between ground stations and satellites, and measured with timing so precise that tiny delays matter. Molecules with many atoms can show wave-like interference when the environment is quiet enough. These are not vague philosophical claims. They are controlled experimental achievements, repeated in different forms, using different technologies, by different laboratories, across decades. And each new test removes one more hiding place for the idea that quantum mechanics is merely a strange story we tell because we do not know better. In fact, one of the most important shifts in modern physics is that quantum weirdness has become practical. It is no longer only a subject for chalkboards and thought experiments. Lasers, transistors, magnetic resonance imaging, atomic clocks, electron microscopes, quantum sensors, and early quantum computers all depend in different ways on principles that would have sounded deeply unnatural to older physics. This does not mean every popular claim about quantum physics is true. Many are exaggerated, mystical, or misleading. But the core experimental reality is stronger than ever. Energy levels really are quantized. Quantum states really can interfere. Measurement really matters. Entanglement really produces correlations that simple, local, hidden variable stories cannot explain. Particles really do behave in ways that cannot be reduced to tiny billiard balls moving along definite classical routes. The weirdness has moved from the edge of theory into the machinery of the modern world. That is what makes it harder to dismiss. If quantum physics were only a set of strange metaphors, it would not let engineers build devices with astonishing precision. It would not let clocks keep time so accurately that satellites, navigation systems, and fundamental physics tests depend on them. It would not let scientists use atoms as sensors so delicate they can detect tiny changes in gravity, magnetism, or acceleration. A wrong theory can sometimes survive for a while by explaining old data, but it cannot keep producing new technologies, new predictions, and new successful experiments across so many different domains, unless it is touching something real. And yet, the mystery has not disappeared. That is the deepest point. Experiments have made quantum physics more certain, but not more intuitively comfortable. They have tightened the evidence without fully satisfying the human desire for a simple picture. You can learn the rules. You can calculate outcomes. You can build devices. You can predict statistics with extraordinary accuracy. But when you ask what is really happening underneath, the old language begins to strain. Is the quantum state a real physical thing or a tool for predicting what we will observe? Does measurement create a definite outcome, reveal one, or split the story into branches? Are probabilities fundamental or signs of something deeper we have not yet understood? Experiments can rule out certain easy answers, but they do not always hand you a comforting replacement. This is why quantum physics feels different from many scientific revolutions. Usually, better experiments make the world clearer in a familiar way. They sharpen the image. They bring the distant object into focus. But here, better experiments often make the mystery cleaner. They remove the fog, and behind the fog is not the old world restored, but a stranger world standing more firmly than before. The uncertainty becomes disciplined. The weirdness becomes measurable. The impossible becomes repeatable. And perhaps that is why this topic is so important for anyone listening. It teaches you what real wonder looks like. Real wonder is not believing every strange claim. Real wonder is watching the strange claims that survive the harshest tests. It is not rejecting skepticism. It is following skepticism far enough that it no longer supports the comfortable answer. Quantum mechanics has been challenged again and again, not gently, not once, but relentlessly. Scientists have tried to expose its weaknesses, refine its predictions, close experimental gaps, isolate systems more carefully, scale them up, compare them across platforms, and make them useful. And through all of that, the core weirdness remains. Not as a rumor, not as a metaphor, not as a spiritual slogan, as data, as technology, as detector clicks, interference fringes, atomic transitions, entangled correlations, and controlled quantum states. The universe, under careful questioning, keeps answering in the quantum language. And the more precise the question becomes, the less easily the answer can be waved away. So when you hear that experiments keep making the weirdness harder to deny, do not imagine science drifting away from reality into fantasy. Imagine the opposite. Science becoming so careful, so exact, so patient, that reality is no longer able to hide behind common sense. The old picture of the world does not collapse because physicists enjoy mystery. It collapses because experiment after experiment keeps pressing on it, and the cracks keep appearing in the same places. What remains is not chaos but a deeper order, one that does not feel natural to the mind at first because the mind was shaped for stones, rivers, faces, and daylight, not atoms, photons, wave functions, and entangled systems. And maybe that is the quiet ending this subject deserves. Quantum physics is not weird because scientists failed to understand the world. It is weird because they understood enough to realize the world was never obligated to match the scale of human intuition. Stern Gerlach reveals spin quantization, A silver atom flying through a magnet once split the old world into two bright marks, and physics has never fully returned from that moment. Imagine it. The year is 1922. The apparatus is delicate, the vacuum is carefully prepared, and a thin beam of silver atoms is sent through a strangely shaped magnetic field toward a cold glass plate. To ordinary intuition, each atom should behave like a tiny spinning object with a magnetic direction that can point at any angle, the way a compass needle might tilt smoothly between north, south, and every position in between. If that were true, the beam should smear into a continuous stripe after passing through the magnet, because some atoms would be deflected a little upward, some a little downward, and many would land in between. Nature should paint a blur, but that is not what Otto Stern and Walter Gerlach saw. Instead of a smooth band, the beam split into two separated spots. Not three, not five, not a soft gradient. Two. It was as if the atoms were being told, in the language of the experiment, that only two answers were allowed. Up or down, one outcome or the other, no in between. This is the shock at the center of the Stern-Gerlach experiment. It revealed that a quantum property connected to angular momentum and magnetic behavior is quantized, meaning it does not vary continuously like the turning of a wheel, but appears in discrete allowed results when measured along a chosen direction. Today, we explain the original silver atom result in terms of electron spin, especially the unpaired outer electron in silver, whose magnetic moment interacts with the non-uniform magnetic field. But the word spin can mislead you if you picture the electron as a tiny planet physically rotating on its axis. Quantum spin is not ordinary rotation. It is an intrinsic property of quantum particles, something built into their identity, with no perfect everyday comparison. The magnet does not reveal a little ball turning clockwise or counterclockwise in the simple sense. It reveals that when this spin-related property is measured along a particular direction, only certain results are possible. The atom's path bends one way or the other because the magnetic field pulls differently depending on that measured spin orientation, and the final plate records the result as two separate traces. The beauty of the experiment is how visual it makes a hidden rule. Quantum physics can sometimes feel like a forest of symbols, but here the message appears as a physical split on a screen. The world at small scales does not always offer a smooth range of answers. Sometimes it offers steps, levels, allowed outcomes, a staircase where common sense expected a ramp. And this was not just a technical detail about silver atoms. It became one of the clearest gateways into the quantum nature of measurement. If you send atoms through one Stern-Gerlach magnet aligned vertically, the beam splits into two groups, which you can call up and down relative to that magnet. If you block one group and keep only the up atoms, then send them through another vertical Stern-Gerlach magnet, they remain up. That seems reassuring, almost classical. The first measurement prepared them. The second confirmed them, but now rotate the second magnet sideways, and the certainty dissolves. The atoms split again into two groups along the new direction. The earlier vertical up result does not contain a complete hidden answer for every possible direction. Measuring one direction prepares the system with respect to that direction, but a different direction asks a different quantum question. And if you then measure vertically again after the sideways measurement, the original vertical certainty can be lost. This sequence is one of the most quietly powerful lessons in quantum mechanics, because it shows that measurement is not merely reading a label already attached to the atom. It can prepare, disturb, and redefine what can be predicted next. The Stern-Gerlach apparatus does not simply sort atoms the way a sieve sorts stones by size. It forces a quantum property into one of the allowed outcomes for the chosen measurement axis. Change the axis and you change the question. Change the question and the pattern of possible answers changes with it. That is why spin quantization matters so deeply. It is not only that particles have discrete values, it is that those values belong to specific measurement contexts. The atom does not behave like a tiny arrow already pointing somewhere definite in ordinary space. waiting for us to discover its exact angle. If that were true, the original beam would have spread continuously. Instead, the experiment gives a strict binary result along the chosen axis, and this helped shape the entire modern understanding of quantum states, superposition, and measurement. Superposition in this setting means that before a particular spin measurement, the system can be described as a combination of possible outcomes for that measurement direction. When the measurement is made, one result appears. But again, we must stay honest. This does not mean the atom is consciously choosing, and it does not mean human eyesight is magically creating the outcome. The measurement is a physical interaction between the atom and the magnetic field, followed by an amplification into a visible trace. The strangeness is not mystical. It is mechanical in the quantum sense, lawful and repeatable, yet foreign to the old classical imagination. In a classical world, a spinning magnetic object could point anywhere and be deflected by any amount. In the Stern-Gerlach world, the atom meets the magnet, and the possible results come in clean, separated channels. This experiment also matters because spin became one of the basic building blocks of modern physics and technology. Electron spin helps explain the structure of atoms, the periodic table, chemical bonding, magnetism in materials, and much of the behavior behind modern electronics. Magnetic resonance imaging, spintronics, quantum computing, and atomic physics all depend in different ways on the reality that spin is not a decorative idea, but a measurable quantum property. The two spots on the plate were not just a curiosity, they were a doorway into the architecture of matter. They showed that the smallest ingredients of the world carry rules that cannot be smoothed into ordinary motion. There is something almost humbling in how simple the original image is. A beam enters, a magnet waits, a plate records, and the result says, the universe does not always answer in shades. Sometimes it answers in permitted outcomes, sharply separated, as if the continuous flow of ordinary experience is built on hidden yes or no foundations. But the deeper lesson is not that everything is binary. Quantum systems can be rich, layered, and probabilistic. The lesson is that nature's allowed answers depend on the property being measured and the way the measurement is arranged. Spin is quantized, but it is also direction dependent. It is discrete, but not classical. It is real, but not a tiny spinning bead. And perhaps that is why Stern-Gerlach remains so unforgettable. It takes one of the most abstract truths in physics and turns it into a visible fork in space. Two marks where there should have been a smear. Two outcomes where continuity was expected. A quiet plate of silver traces, saying that the world beneath the world is not made from smooth certainty, but from allowed possibilities becoming definite under the touch of measurement. So when you hear that Stern-Gerlach reveals spin quantization, do not picture a complicated equation first. Picture a beam of atoms entering a magnet and emerging as two separated streams, as if nature itself drew a line through common sense. And in that split, you are seeing one of quantum physics' clearest messages. Matter is not only made of particles, but of rules that decide which answers reality is allowed to give. Superconducting circuits show artificial atoms. An atom can be grown from metal lines on a chip, not by copying nature's nucleus, but by teaching electricity to obey quantum rules. Imagine a tiny circuit resting inside a refrigerator colder than deep space, cooled until ordinary electrical noise becomes quiet enough for something delicate to appear. At room temperature, a circuit is a practical object. Current flows, voltage changes, signals move, and everything feels classical, predictable, engineered. But when certain metals become superconducting, their electrical resistance drops away, and the circuit begins to behave less like a messy river of individual electrons and more like one coordinated quantum system. Now add a Josephson junction, a thin, insulating barrier placed between two superconductors, so thin that pairs of electrons can tunnel through it, according to quantum mechanics. This small junction gives the circuit the crucial ingredient ordinary circuits lack: nonlinearity. Without that nonlinearity, the circuit would be like a simple harmonic oscillator with evenly spaced energy levels, useful but not enough to isolate two levels as a controllable quantum bit. With the Josephson junction, the energy levels become unevenly spaced, more like the discrete levels of an atom, so scientists can use microwaves to address one transition without accidentally exciting all the others. That is why these devices are often called superconducting artificial atoms. They are not atoms in the chemical sense. They have no nucleus surrounded by natural electron shells. They are human-designed electrical circuits, often visible under a microscope, patterned onto chips with lithography. Yet they can absorb and emit microwave photons at specific frequencies, occupy quantum superpositions, and interact with resonators in ways that resemble how real atoms interact with light. Reviews of circuit quantum electrodynamics describe how Josephson junction circuits enabled macroscopic electrical systems to display quantum effects and act as artificial atoms coupled to microwave cavities. This is where the strangeness becomes almost inverted. Instead of finding quantum behavior only by shrinking down to nature's smallest ingredients, scientists build a structure large enough to be engineered and wired, then cool and isolate it until it reveals atom-like quantum behavior on demand. A natural atom is given by the universe. Its energy levels come from the laws of electromagnetism and the structure of its electrons. An artificial atom is designed. Its personality can be shaped by choosing capacitance, inductance, junction energy, geometry, and materials. A transmon qubit, one of the most widely used superconducting qubits, is built to reduce sensitivity to charge noise, while keeping enough enharmonicity to behave like a useful two-level system, and it has become a central workhorse of superconducting quantum computing. Think of the difference like this. A natural atom is a wild bird whose song you learn to recognize. An artificial atom is a musical instrument you build so it can sing one carefully chosen note when struck with a microwave pulse. The note is quantum. The instrument is engineered. And when that artificial atom is placed inside or near a microwave resonator, the resonator becomes like a tiny echo chamber for microwave photons. The artificial atom and the resonator can exchange energy, shift each other's frequencies, and allow scientists to read the qubit's state without simply destroying it immediately. This field, called circuit quantum electrodynamics, borrows ideas from atomic physics and quantum optics, but moves them onto a chip, where microwave photons replace visible light and superconducting circuits replace natural atoms. The result is a laboratory where quantum behavior can be designed, tuned, scaled, and measured with electronic control. That control is the reason superconducting circuits became one of the leading platforms for quantum processors. A qubit is not just a tiny switch that is either 0 or 1. It can be prepared in a quantum combination of its two lowest useful energy states, manipulated with microwave pulses, entangled with neighboring qubits, and measured through the resonator or readout circuitry. But this power comes with fragility. The artificial atom must be protected from heat, stray radiation, material defects, vibrations, unwanted photons, and microscopic noise sources that can steal its coherence. Coherence is the time during which the qubit keeps its quantum phase relationships alive. If that coherence fades too quickly, the qubit forgets the delicate information it was meant to carry. This is why superconducting quantum computers are not simply ordinary computers made colder. They are careful ecosystems, cryogenic refrigerators, microwave lines, shielding, filters, amplifiers, control electronics, and chips whose materials must be cleaner and quieter than everyday engineering ever required. The artificial atom is powerful precisely because it is both quantum and built. But because it is built, every imperfection matters. A tiny defect in a material, a microscopic surface loss, a stray microwave photon, or a poorly isolated control line can become the environment's way of asking the qubit a question too early, forcing the fragile state to decay. And yet, despite all this difficulty, the progress has been remarkable. Superconducting circuits have allowed scientists to create controllable artificial atoms, couple them together, perform quantum gates, study light-matter interaction in regimes difficult to reach with natural atoms, and build processors with many qubits on a chip. The artificial atom is not a metaphor anymore. It is a working quantum device. It turns the abstract rules of quantum mechanics into something engineers can tune with wires and pulses. There is something quietly profound in that. Nature gave us atoms, but humans learned to build atom-like systems from circuits. We did not make them alive, and we did not make them mystical. We made them obey. We carved islands of quantum behavior into metal and insulation, cooled them until thermal chaos fell silent, then used microwaves to speak to them in the language of energy levels. And maybe that is why superconducting circuits feel like one of the most human forms of quantum physics. They are not found in a distant galaxy or hidden inside an ancient crystal. They are designed on screens, fabricated in cleanrooms, mounted in refrigerators, connected by cables, and tested through patient repetition. They show that quantum strangeness is not only something we discover, it is something we can engineer if we respect how delicate it is. So when you hear that superconducting circuits show artificial atoms, do not picture a fake atom pretending to be real. Picture a tiny frozen circuit whose electrical energy comes in discrete steps, whose transitions can be driven by microwaves, whose state can store quantum information, and whose behavior proves that atom-like does not have to mean born inside nature's periodic table. Sometimes an atom is not a little sphere in space. Sometimes it is a carefully designed rhythm of current and phase, held inside a circuit cold enough for the ordinary world to grow quiet. And in that quiet, a human-made object begins to behave as if it has joined the quantum architecture of matter itself. Trapped ions act like controlled quantum systems. A single charged atom can be held almost motionless in empty space, like a grain of matter suspended inside an invisible cage. And once it is quiet enough, scientists can make it behave like one of the most controllable quantum systems ever built. Imagine taking an atom, removing or adding an electron so it becomes electrically charged, then placing it inside carefully shaped electric fields that keep it floating without touching any surface at all. It does not sit on a wire. It does not rest on a chip. It does not need a tiny shelf. It is trapped by fields held in a vacuum so clean that stray air molecules almost never collide with it, and cooled with lasers until its motion becomes incredibly slow, close to the lowest energy allowed by quantum mechanics. This is the world of trapped ions, and it feels almost impossible because it turns one of the smallest pieces of matter into something scientists can isolate, address, move, read, and manipulate with extraordinary precision. The trap is usually a device such as a Paul trap, which uses oscillating electric fields to confine the ion, because static electric fields alone cannot hold a charged particle stably in all directions. In the right arrangement, the ion settles into a tiny region of space, not perfectly still in the everyday sense, but controlled so well that its motion, internal energy states, and interactions can be treated as tools rather than noise. This matters because a useful quantum system must be both fragile and controllable, and that combination is rare. If a system is too isolated, you cannot operate it. If it is too exposed, the environment ruins it. Trapped ions sit beautifully between those extremes. They can remain coherent for a long time compared with many other quantum platforms. Yet lasers and microwave fields can still speak to them with fine control. A trapped ion can store a qubit in two long-lived internal states, often two energy levels of the ion that can represent the two basic alternatives of quantum information. But unlike an ordinary bit, the ion's qubit can be prepared in a superposition, a carefully controlled blend of those alternatives, and several ions can be entangled, so their states become linked in a way that has no classical equivalent. The remarkable part is how scientists control them. Laser beams can cool the ions, prepare their states, rotate their qubits, couple their internal states to their motion, and finally read them out. Reading an ion can be surprisingly visual. Under the right laser light, one state may scatter photons and appear bright to a detector, while another state remains dark, so the answer can become a tiny glow, a single atom announcing its quantum state by whether it shines. But before that glow, there is a whole hidden choreography. If several ions are trapped together, they naturally arrange themselves into a line or crystal because their electric charges repel one another while the trap confines them. They sit like beads in an invisible bowl, not touching, but linked by their shared motion. That shared motion becomes one of the great strengths of trapped ion quantum computing. You can use the collective vibration of the ion chain as a kind of quantum bus, a way for one ion state to influence another under carefully timed laser pulses. The ions are separated enough to address individually, yet connected enough through their motion to perform entangling gates. This is very different from the image of wires carrying current between classical computer parts. In a trapped ion processor, connection can be mediated by motion itself, by the way the entire little crystal trembles in quantized patterns. The qubit may live in internal energy states, while the interaction between qubits is created through shared vibrational modes. That is why cooling the motion matters so deeply. If the ions are moving too thermally, too noisily, then the shared bus becomes messy. Laser cooling, including sideband cooling in many experiments, can bring selected motion close to its quantum ground state, making the vibrations cleaner and more usable. From there, carefully shaped laser pulses can perform logic operations, create entanglement, and run small quantum algorithms. Trapped ions are also powerful for quantum simulation, where the goal is not necessarily to build a general-purpose computer immediately, but to use a controllable quantum system to imitate another quantum system that would be too hard to calculate directly. Chains of ions can simulate magnetism, phase transitions, particle interactions, and other many-body behavior by engineering how the ions affect each other. In that sense, trapped ions become a tiny model universe, not because they literally contain the system being studied, but because their quantum rules can be tuned to mirror important features of it. This is one of the deepest promises of the platform. Instead of forcing an ordinary computer to approximate a quantum world from the outside, scientists create a cleaner quantum world inside the lab and let it evolve under known rules. But trapped ions are not perfect, and the honest story must include the difficulties. Laser control must be stable. Motional modes can become crowded as more ions are added. Operations can slow down compared with some solid-state systems. Heating of ion motion, imperfect pulses, scattered light, crosstalk between neighboring ions, and technical noise all have to be managed. Scaling from a few excellent ions to thousands or millions of useful qubits is a huge engineering challenge. Researchers explore modular architectures, shuttling ions between trap zones, connecting separate ion traps with photons, and improving control systems so larger devices can be built without losing the precision that makes trapped ions so attractive. So the beauty of trapped ions is not that they make quantum computing easy. Nothing does. The beauty is that they make quantum control feel almost personal. You are not handling a vague cloud of material. You are holding individual atoms in place, cooling them, shining laser light on them, listening to their fluorescence, and using their motion as a bridge between invisible states. It is one of the closest things physics has to touching a quantum object without turning it back into ordinary chaos. And trapped ions have another remarkable role beyond computing. They are used in some of the world's most precise clocks. Certain ion transitions are so stable that they can serve as extraordinarily accurate time references. In those experiments, the ion is not only a qubit-like system, it becomes a tiny pendulum of nature, an atomic rhythm so consistent that it can test gravity, relativity, and the passage of time itself with astonishing sensitivity. This shows how broad the trapped ion idea really is. The same control that lets scientists build quantum gates also lets them measure time, forces, fields, and fundamental constants with incredible precision. At the heart of all of this is one simple but profound achievement. A single atom, normally part of the restless heat and collision of the world, has been separated, cooled, held, and made to follow instructions. Not crude instructions, but quantum instructions. It can be placed into superposition. It can be entangled with a neighbor. It can glow or remain dark depending on its state. It can share motion with other ions, like a small crystal breathing in unison. And every time this happens, the experiment reminds you that quantum mechanics is not just a set of strange ideas hiding in equations. It is something that can be engineered with such care that one atom becomes a controllable instrument. So when you hear that trapped ions act like controlled quantum systems, do not picture atoms trapped helplessly like insects in glass. Picture charged atoms held gently in empty space, protected from the noise of the world, cooled until their motion becomes a clean quantum resource, and guided by lasers with almost musical precision. They are small but not simple. They are fragile but not unreachable. They are natural particles turned into human-controlled quantum tools. And in their quiet glow, you can see one of the most hopeful sides of quantum science. The weirdness is not only something we observe from a distance. With enough patience, discipline, and respect for delicacy, it is something we can learn to hold steady. Quantum dots behave like artificial atoms. A crystal so small it begins to act like an atom is one of the quietest ways matter reveals that size can rewrite identity. Imagine taking a piece of semiconductor material, the kind of material used in electronics, screens, sensors, and solar cells, and shrinking it down until it is only a few nanometers wide, so small that the electrons and holes inside it no longer have room to move as freely as they would in a larger solid. At ordinary scales, a semiconductor behaves more like a landscape with broad energy bands, allowing charges to move through many available states. But when the same material is squeezed into a tiny region in all three dimensions, the charge carriers become confined, almost like a wave trapped inside a very small room. And when waves are trapped, only certain patterns fit. This is the heart of a quantum dot. It is not an atom, because it is not built around a single nucleus with natural electron shells. It is usually a tiny semiconductor crystal or a nanostructure made by human design. Yet because confinement forces its electronic energies into discrete levels, it can behave in atom-like ways, which is why quantum dots are often called artificial atoms. They absorb and emit light at specific energies. They can hold individual electrons or excitons, and their properties can be tuned by changing their size, shape, material, or surrounding structure. The smallest change in size can shift the color of light they emit, because a smaller dot confines the electron and hole more tightly, raising the energy of the emitted photon, while a larger dot usually emits lower energy, redder light. This size-dependent color is one reason quantum dots became famous beyond physics laboratories. They appear in display technology, LED lighting, biological imaging, and optoelectronics, and the 2023 Nobel Prize in Chemistry recognized their discovery and development for exactly these nanoscale quantum size effects. But the phrase artificial atom points to an even deeper story than glowing screens. A natural atom has discrete energy levels because electrons are bound by the electric pull of the nucleus. A quantum dot has discrete energy levels because electrons or electron hole pairs are confined by a nanoscale boundary, gate voltages, material interfaces, or the physical size of the crystal. In both cases, the charge is not free to take any energy at once. Only certain quantum states are allowed. That analogy is real, but it must be handled carefully. A quantum dot is not a fake hydrogen atom, and it does not copy the periodic table in a simple way. Its atom-like behavior is engineered. Scientists can tune its confinement, connect it to electrodes, place it in optical cavities, embed it in devices, or grow it with a protective shell to improve its light emission. Some quantum dots are colloidal nanocrystals made in solution, so small they can be processed almost like chemical materials. Others are lithographically defined structures in semiconductor devices, where electric gates can control how many electrons enter the dot, sometimes one by one. In these gate-defined dots, researchers can create a situation where adding a single electron costs a measurable energy, producing effects like Coulomb blockade, and the dot can be used to study single-electron physics, or even serve as a spin qubit for quantum information. Quantum dots are described as artificial atoms because they confine electrons with discrete energy levels. and researchers can engineer their coupling and interactions in quantum dot arrays, making them useful building blocks for artificial materials and quantum devices. This is where the idea becomes especially beautiful. A quantum dot does not merely shrink matter, it gives matter a new rulebook. The same substance can behave differently when its size approaches the scale of the electron's quantum wavelength. Gold does not become a new element when made small, but many materials at the nanoscale reveal properties that are not obvious in the bulk. Quantum dots are among the clearest examples because their color and electronic structure can be tuned almost like turning a dial. In a large semiconductor crystal, many energy states crowd together into bands. In a dot, the allowed states separate enough that the dot begins to behave more like a tiny artificial shell system. That is why scientists sometimes speak of shell filling in quantum dots, echoing atomic orbitals, though the exact shapes and energies depend on the dot's geometry and confinement potential rather than a natural nucleus alone. The word artificial here should not make the behavior feel less real. A bridge is artificial, but gravity acting on it is real. A flute is artificial, but the notes it produces are real. A quantum dot is artificial, but the quantized energy levels inside it are real consequences of quantum mechanics. Human beings design the boundary. Nature supplies the rule that only certain wave patterns fit inside. That partnership between design and law is what gives quantum dots their power. They are small enough to show discrete quantum behavior, but large enough and flexible enough to be built into devices. They live between atoms and ordinary solids, carrying something of both worlds. They can behave like tiny light emitters with tunable colors, like single-photon sources in quantum optics, like charge islands in electronic transport, or like controllable qubits when individual spins are isolated and manipulated. And yet they are fragile in their own way. Surface defects can trap charges and reduce brightness. Variations in size can broaden their emission. Environmental noise can disturb the spin state of an electron. Materials must be carefully chosen, shells engineered, interfaces cleaned, and devices cooled or stabilized depending on the application. The artificial atom is not a toy atom that simply works because the phrase sounds elegant. It is a demanding quantum object whose usefulness depends on controlling confinement, noise, and coupling with great care. That honesty matters because it makes the wonder stronger. Quantum dots are not magical specks sprinkled into technology. They are physical systems where electrons are forced to reveal how deeply their behavior depends on space, boundary, and scale. And perhaps this is the most important thing a listener can learn from them. Identity in matter is not always fixed by composition alone. Size can change behavior. Shape can change energy. Confinement can turn a piece of semiconductor into a tiny artificial atom with its own spectrum of possible states. This is a profound shift from ordinary thinking. We often imagine that a material is what it is because of what it is made of. And that is true in one sense. But quantum dots show that how matter is arranged, how tightly it is confined, and how much room its electrons have can be just as important. A small enough crystal can glow a different color, not because it has become chemically different, but because quantum confinement has changed the allowed energies inside it. In that sense, quantum dots are like small rooms where the architecture decides the music. Make the room smaller and only shorter, higher energy notes fit. Make it larger and the notes deepen. The material is the instrument, but size tunes the song. So when you hear that quantum dots behave like artificial atoms, do not picture a miniature solar system or a fake copy of nature's atoms. Picture a nanoscale island of semiconductor where electrons are confined so tightly that their energies become separated into allowed steps, where light can be absorbed and emitted with tunable precision, where single charges can be counted, and where engineers can shape quantum behavior by designing the dot itself. It is not an atom born from a star. It is an atom-like system born from confinement. And in that tiny island, matter teaches a gentle but radical lesson. Sometimes the smallest boundaries create the clearest colors, and sometimes by making the world smaller, we do not reduce its mystery. We give the mystery sharper edges. Cold atoms simulate impossible materials. Some materials are too strange to build in nature, so scientists learn to create their shadows from atoms colder than almost anything in the universe. Imagine a cloud of atoms floating inside a vacuum chamber. Not hot, chaotic, and fast like the air around you, but slowed down by lasers until their motion becomes almost unbelievably gentle, as if matter itself has been asked to breathe more slowly. At everyday temperatures, atoms race in every direction, colliding, vibrating, carrying too much thermal noise for their delicate quantum behavior to stay visible. But when atoms are cooled to temperatures only tiny fractions above absolute zero, the noise falls away, and something extraordinary becomes possible. Scientists can begin using those atoms like controllable building blocks in a model world. This is the heart of cold atom quantum simulation. The goal is not to make a tiny copy of a material atom by atom in the ordinary engineering sense. The goal is to create a clean, adjustable quantum system that follows the same kinds of rules as a complicated material that would be nearly impossible to understand directly. Many real materials, especially the most interesting ones, are too complex for even powerful computers to fully calculate because their electrons interact with one another in deeply quantum ways. In a metal, an insulator, a magnet, or a superconductor, huge numbers of particles are constantly influencing each other, and the number of possible arrangements grows so quickly that classical calculation can become overwhelming. Cold atoms offer a different approach. Instead of forcing a normal computer to imitate a quantum material from the outside, scientists build another quantum system in the laboratory and let it imitate the material from the inside. This idea goes back to Richard Feynman's famous insight that nature is quantum. So the most natural way to simulate quantum nature may be with another quantum system. Cold atoms are especially powerful for this because they are unusually clean. In a real solid, electrons move through a messy landscape of impurities, vibrations, defects, and uncontrolled interactions. But in a cold atom experiment, researchers can trap neutral atoms with laser light, arrange them in repeating patterns called optical lattices, and tune how strongly they move or interact. An optical lattice is not a crystal made of physical walls. It is a crystal made of light. Crossing laser beams form a standing wave, creating a pattern of bright and dark regions that acts like an invisible egg carton for atoms. The atoms settle into the light-made wells, and suddenly, you have something that resembles electrons moving through the regular structure of a solid, except now the solid is made from light and can be adjusted almost like a control panel. Make the lattice deeper, and atoms have a harder time hopping from one site to another. Change the interactions, and atoms repel or attract differently. Change the geometry, and you can create square lattices, triangular lattices, honeycomb lattices, or more exotic arrangements. This is why the phrase impossible materials matters. Scientists are not limited to materials that happen to exist in the ground. They can design artificial quantum worlds with rules that are difficult or impossible to find naturally. Then watch how atoms behave inside them. One of the most famous examples involves the Bose-Hubbard model, a simple-looking but deeply important model describing particles hopping between lattice sites while interacting with each other. With cold atoms in optical lattices, scientists were able to observe a transition between a superfluid-like state, where atoms flow collectively through the lattice with shared quantum coherence, and a Mott insulator state, where atoms become locked into place because interactions make movement energetically costly. This is a beautiful example, because it shows how a material can change identity, not because its atoms are chemically different, but because the balance between motion and interaction has changed. When movement dominates, the atoms behave collectively, almost like a smooth quantum fluid spread across the lattice. When interaction dominates, they become localized one by one, as if the lattice has frozen them into a pattern of restraint. This kind of transition is not just a laboratory trick. It helps scientists understand why real materials can switch between conducting and insulating behavior, why interactions matter, and why quantum matter cannot always be understood by thinking about particles independently. Cold atoms also allow researchers to explore artificial magnetism, even though the atoms are neutral and do not naturally feel magnetic fields the same way electrons do in a solid. By using lasers, rotation, or carefully engineered phases in the atom's motion, scientists can create synthetic gauge fields, which make neutral atoms behave as if they are moving in a magnetic environment. This opens the door to simulating quantum Hall physics, topological states, and other exotic forms of matter, where the global shape of the quantum state matters as much as local motion. Topological materials are especially fascinating because some of their properties are protected by the structure of the state itself, making them resistant to certain kinds of disturbance. Cold atoms can help researchers explore these ideas in clean settings, where parameters can be changed slowly and deliberately. They can also simulate frustrated magnetism, where particles or spins cannot all satisfy their preferred arrangements at once, producing rich and unpredictable behavior. In ordinary magnets, tiny magnetic moments tend to align in patterns, but in frustrated systems, the geometry prevents all interactions from being simultaneously satisfied, like trying to arrange people around a table so everyone sits next to their preferred neighbor, while the table shape makes it impossible. The result can be a quantum state with no simple frozen order, a restless compromise that may resemble the mysterious behavior of quantum spin liquids. Cold atoms give scientists a way to build these difficult geometries and study what happens without needing to discover a perfect natural crystal first. But the honesty of the science matters here. Cold atoms do not magically solve every problem. They are not universal answers to all materials. They often simulate simplified models, not full real-world substances with every chemical detail included. They require extreme cooling, vacuum systems, lasers, magnetic fields, careful calibration, and complex detection methods. They can be hard to scale, hard to measure without disturbing, and hard to connect directly to a specific material in your hand. Yet their strength lies exactly in that simplification. A good simulator does not reproduce every messy feature of the world. It isolates the rule you want to understand. It builds a clean version of the problem so the hidden mechanism can show itself. And perhaps this is the deeper lesson cold atoms teach. Sometimes, to understand reality, you must make a quieter version of it. You must remove the dirt, the heat, the collisions, the accidental complexity until the core behavior can be seen. In a cold atom laboratory, matter becomes almost meditative. Atoms are slowed, arranged, and guided into patterns of light. They are not forced into being ordinary solids. They are allowed to become models of what solids could be under stranger laws. They can imitate insulators, fluids, magnets, and topological phases. They can test ideas that would otherwise live only in equations. They can make invisible models breathe in the real world. And there is something deeply beautiful about that. The universe gives us atoms, but with enough care, we can ask those atoms to become metaphors with physical weight, small experimental worlds that teach us how larger worlds might behave. So when you hear that cold atoms simulate impossible materials, do not imagine scientists creating fantasy crystals for spectacle. Imagine a cloud of matter cooled until its restlessness nearly disappears, placed inside a lattice made of light, tuned until motion, interaction, geometry, and coherence begin to tell a new story. These atoms are not pretending. They are obeying quantum rules in an environment humans designed. And by watching them, scientists learn what kinds of matter might exist, what phases nature could allow, and why the solid world beneath your feet is only one small region in a much larger landscape of quantum possibility. SQUIDs measure tiny magnetic changes. Quantumly, a magnetic change too small for ordinary instruments to notice can still bend the rhythm of a superconducting loop. Imagine a device so sensitive that it can listen for magnetic whispers from the human brain, from the heart, from tiny currents in materials, from geological signals under the ground, and from experiments where the difference between knowledge and noise may be almost unimaginably thin. This device is called a SQUID, a superconducting quantum interference device, and despite the playful name, it is one of the most sensitive magnetic sensors ever made. Its power comes from a strange partnership between two quantum ideas, superconductivity and interference. In a superconducting material, when it is cooled below a critical temperature, electrical resistance disappears, and electrons do not move as ordinary independent particles anymore. They form paired quantum states that can flow together through the material without losing energy as heat. Now shape that superconductor into a loop and interrupt it with one or two Josephson junctions, which are extremely thin barriers where superconducting pairs can tunnel across in a quantum way. Suddenly, the loop becomes more than a wire. It becomes a sensor whose behavior depends delicately on magnetic flux, the amount of magnetic field threading through the loop. A DC SQUID typically uses two Josephson junctions in a superconducting loop, while an RF SQUID uses one junction, and both rely on the fact that superconducting phase and magnetic flux are tied together in quantized ways. SQUIDs use Josephson effect phenomena to measure extremely small variations in magnetic flux, and reviews describe them as among the most sensitive magnetic flux detectors available. The central idea is gentle if you picture it carefully. In the superconducting loop, the quantum wave describing the paired electrons must fit around the loop in a consistent way, almost like a song that must close on itself without a broken note. When a magnetic field passes through the loop, it shifts that quantum rhythm. The shift changes how current can pass through the Josephson junctions, and that change can be converted into a measurable voltage or signal. In other words, the SQUID does not measure magnetism the way a compass needle does, by visibly turning toward north. It measures how magnetism changes the phase relationship inside a superconducting quantum circuit. That is why tiny magnetic changes can become detectable. The device is not merely amplifying a weak field like a microphone amplifies a quiet voice. It is using quantum interference itself as the listening mechanism. A magnetic field slightly changes the relationship between the two paths around the loop, and the SQUID responds with a periodic change in its output. This is why the word interference belongs in its name. It is not optical interference with light, but quantum interference in a superconducting circuit. The superconducting wave can go around the loop through different branches, and the magnetic flux changes how those branches combine. A tiny change in flux shifts the pattern, and from that shift, scientists infer the magnetic change. The relevant unit is the magnetic flux quantum, an extremely small package of flux set by fundamental constants, and SQUIDs are built to notice fractions of that scale. The result is a sensor capable of detecting magnetic fields so faint that they would be completely drowned out in ordinary measurement. A SQUID can reach sensitivities in the femtotesla range under the right conditions, which is tiny compared with everyday magnetic fields. For context, the magnetic fields produced by biological activity in the brain and heart are far weaker than a refrigerator magnet. Yet SQUID-based biomagnetism systems have been used to detect such signals. This does not mean a SQUID is magical or easy to use. It usually requires cryogenic cooling, often with liquid helium or specialized cryocoolers, because superconductivity has to be maintained. It must be shielded from environmental magnetic noise, because the world is full of unwanted signals. Power lines, elevators, cars, phones, moving metal, even the Earth's magnetic field. It often uses pickup coils and gradiometers to reject common background noise and focus on the tiny signal of interest. The surrounding system can be as important as the SQUID itself. A sensor. This sensitive does not live comfortably in the ordinary world. It has to be protected from it, and yet, when it is protected well, it becomes almost uncanny in what it can hear. In magnetoencephalography, or MEG, arrays of SQUID sensors have been used to measure the weak magnetic fields produced by neural activity in the brain, giving researchers millisecond-level timing information about brain function. In magnetocardiography, similar ideas can detect magnetic fields generated by the heart. In materials science, SQUID magnetometers measure the magnetic properties of samples as temperature, pressure, or applied magnetic field changes. In geophysics, they can help detect subtle magnetic variations related to minerals or underground structure. In fundamental research, SQUIDs can read out other sensitive cryogenic detectors and help explore phenomena where tiny changes in magnetic flux carry important information. SQUID magnetometers are used across biomagnetism, materials measurement, microscopy, and cryogenic detector readout, including applications such as MEG and magnetic imaging. What makes the device especially beautiful is that it is a macroscopic quantum instrument. It is not a single atom hidden in a vacuum chamber. It is a human-made circuit, large enough to fabricate and connect to electronics, yet its operation depends on a shared quantum phase extending around a loop. The quantum effect is not confined to the invisible interior of a particle. It becomes part of a working measurement device. That is why SQUIDs feel like a bridge between the microscopic and the human-built world. On one side, there is the delicate quantum behavior of superconducting pairs and Josephson tunneling. On the other side, there is a real instrument on a lab bench, reading magnetic signals from brains, materials, sensors, and experiments. The quantum world is not only something to be observed, it can become the ear with which we observe other things, and this changes the way you think about sensitivity. Ordinary measurement often feels like looking for a large motion, a visible displacement, a needle swinging across a dial. A SQUID teaches a quieter method. It listens for a shift in phase, a tiny change in flux, a near invisible alteration in the rhythm of a superconducting loop. It is a reminder that some of the most important changes in nature do not announce themselves loudly. They do not shake the room. They do not flash across the sky. They slightly retune the hidden pattern of a quantum circuit, and if the instrument is delicate enough, that retuning becomes a signal. So when you hear that SQUIDs measure tiny magnetic changes quantumly, do not picture a strange creature or a simple metal detector. Picture a superconducting loop cooled into quietness, interrupted by Josephson junctions, waiting for magnetic flux to shift its quantum phase. Picture a device that turns interference into measurement, and measurement into a way of hearing fields too faint for ordinary instruments to sense. In the end, the SQUID is not only a sensor, it is a lesson in how the universe can make the invisible measurable, not by making the signal louder, but by making the listener quantum.